So let's start with the topic itself. This is a module which walks us through the overview. That means gives you an idea about the product in its entirety. And then later we'll go through the details of the product. So first and foremost, what is the thing that is brought to mind? What do you associate the word SDN with? So I have software defined networking. That's the acronym. And as soon as you hear the term, what does it bring to mind? What? You know, when you hear the term, it should mean something. So what does it mean? Some of you have some interpretation, some of you probably don't. But anybody who does have some interpretation of software-defined networking.
So this is Greg. My interpretation is the ability to interact and manage a network infrastructure via programming or programmability, as opposed to having like a CLI interaction with individual devices and so forth. It becomes, you somewhat abstract the hardware, and it's all done via like a software interface, whether it's automated programming or GUI.
Okay, thank you, Greg. And I think Victor may have been trying to convey kind of the same thing. It's more application driven, so more software driven. Anybody else with any other interpretations?
Felipe?
Yes, Felipe.
It's basically, the way I see it is multiple systems or devices giving you software like ICE or DNA is one of those, right? That I have seen that may play a part in that, in the software.
Okay.
So basically, I guess it's a collaboration of systems doing it.
Okay. Yes, I mean, if you look at the entire architecture, there's several systems doing it. I am going to break it down in a little bit more detail. So we have a kind of like a comparison and analogy of how things used to be in the past and how SDN is changing the trend. Okay. Now, something I do want to remind each one of you, while you're not speaking to us in the classroom, keep your end muted. And the reason is, over the years, we tend to, we do record this class, so you do have access to this information for 12 months from now. And over the years, we've had different things recorded in our recording. Some students complained that it would have been a student and his spouse or her spouse having an argument being recorded. The reason is that person was not muted. See, when I'm delivering the class, I can mute everybody with one button, but if I'm not at my desk and I've just stepped away for a break or something and somebody's unmuted, and it does happen to me also. Last week when I was talking to my doctor while we were on a break, my end was not muted, and then a student had to remind me that my mic got unmuted. So just be a little careful. It may be things that you don't want others to hear. It could be some discussion at work. But since this gets recorded, any audio, gotta be careful about keeping yourself unmuted. I don't have a choice. I'm an instructor, so I really have to unmute myself. But until the student reminded me last week via chat window, and I really appreciate him having done that because I was discussing some health issue with my doctor while on a break. So just be a little careful, okay? Let's take it from there. Let's compare these different vendors. Now, we'll tell you that this term, SDN, it was coined around 2000, 2006 timeframe, started then. And one of the people credited with the solution for software-defined networking, or the lead team, was based out of Stanford. This individual named Martin Casado. Okay, he actually came up with a protocol and thus a solution for SDN. Okay, software-defined, which definitely means, as every one of you mentioned, a software-based solution, something that you would do through a GUI or through programmability, a solution to get some bunch of devices working. And it may help to kind of contrast Cisco's SDN solution with some other vendors. If you can distinguish between the two terms that we have used in networking over the years, control plane and data plane. Anyone aware of the difference between these two terms? What do we mean by that? Control plane. Let's look at what control plane means, and then we'll look at what the data plane means. Anyone aware of the difference?
This is Greg. Typically, the control plane is the data bus that manages the system, supervisory packet, time in, decoding, demultiplexing, and things like that. That's typically what the control plane consists of.
Okay, and that is, okay, great explanation, Greg. Control plane consists of those which manage the system. Can I go ahead and even add on to it? Maybe control plane is the bunch of protocols involved in making routing decisions or switching decisions. Those protocols which help establish this fib, rib, MAC address table, all of those contributors to building those tables and helping make the decision within the device would be your control plane. Okay. Our data plane, what would that be?
That would be the bus that carries the actual data packets for the most part. So whatever's been sent by the end devices to the server, like the client server traffic.
Okay, thank you, Greg. The plane that carries, or I would say most of the interfaces are essentially the ports, the interfaces on the devices are typically associated with data plane because they move the data traffic between the client server or server to server. It could be north-south traffic or east-west traffic. That would be part of data plane. So I'm going to say if I take a vendor like VMware, these devices are called the NSX controllers. And I would also write in parentheses saying those are centrally controlled or centralized devices. The data plane, if I were to work with a VMware environment, would be your software switches. So, or virtual switches. And then I'm going to write the word there, distributed. Now, when we talk about Cisco's SDN solution, and then VMware has what they call a separate set of management plane devices. They call the NSX managers. And these are also centralized. So I'm going to use the word centralized. Now, I hope you can, or everybody distinguishes between the management plane and control plane. Everybody got that difference in your mind figured out? The difference between a management plane and a control plane. Everybody squared away that difference. Hopefully, I assume. So control plane is your routing and switching protocols. Your management plane is the component that involves configuration control. So the devices or the component within the device that allows an administrator to step in and make changes. That would be the management plane. And in Cisco ACI, the contrast is the control plane is, I'm going to say, distributed. In every switch. Would that be right? Am I accurate here or am I misleading you? Control plane is distributed.
I would say that's accurate.
Sounds accurate?
Yes.
Okay, thank you, Greg. Data plane is distributed also. And management plane is the only one which is centralized. Everybody see the difference between the most vendors? I just cited VMware and Cisco. Notice the difference. Okay. Now here, I'll go ahead and emphasize a bit more on the centralized management plane. It is so true that you cannot configure these switches individually. There is a command line, but there is no config T prompt. There is no configurable option on these switches. You can only manage this environment through their APIC servers. That's the only management plane. Okay, but clearly it appears that all the routing and switching protocols run on every switch. But configuration is completely done via these APIC servers. Okay. So that's a stark difference between Cisco and most other SDN solutions. Ask me why Cisco took this approach. Why Cisco did not go with a centralized control plane.
The APICs could go down, but we'd still keep our data center up.
Sorry, Derek, what did you?
I assume that because our APICs could go down, but our data center would stay up, even if we lost our APIC. Yeah.
So thank you. APICs could go down, the data center would stay up. You see what they're saying? What Derek mentioned, your centralized control plane, there is no centralized control plane. Okay. Cisco also looked at another aspect, scalability. You must remember Cisco's ACI solution was available for sale only after VMware NSX. NSX was there probably a year and a half or 2 years before Cisco offered the ACI solution. Cisco stepped in a little late into the data center software-defined networking arena, but they did observe one of the drawbacks of VMware: scalability. Very, very large environments, NSX could not scale with control plane being centralized. Hence, Cisco decided to take a different approach. Now, no doubt, things have changed. Cisco's approach, adopted in 2014, they announced 2013, but there have been a lot of improvements in protocols in the last 5 years, so things have changed. We may just trend towards a centralized control plane, but not yet. Not in a very scalable environment. Okay, they may just trend towards that in the future, but not yet. Okay, so at this point, the routing protocols, the switching protocols run on every switch. Okay. Now, ACI, application-centric infrastructure. That term itself is saying, well, your infrastructure should revolve around the need of the application. That means application requirements is going to dictate the way you lay out your infrastructure. That's just the definition of the term. Okay. So you will learn how this network is to be designed, and of course, what are the building blocks? Okay, right there, application-centric infrastructure. Now, applications nowadays are 2-tier, 3-tier, okay, tiers. Notice I say multi-tier. Well, you might just ask me, do network engineers now need to be aware of application requirements and the number of tiers? And I'm going to say, yes. Okay. Yes, you should be aware of it. That's what would help you design your application-centric environment. In the past, we have used what's called network-centric environments. Not the trend anymore. Looking forward, it's going to be application-centric. Everything that you design will be based on how many tiers in the application, what type of communication between the different tiers. So that's going to be the future. Okay. It does use the time-tested routing protocols and switching protocols, no doubt. It has to use that with emphasis on, hey, high speed, low latency, the fact that we have multiple links, scalable, fault-tolerant architecture, high bandwidth links. That's all the emphasis, no doubt. But from a design perspective, application-centric. Okay. Multi-tier application maybe. It could be virtualized applications. It could be container applications. It could be traditional bare metal-based applications. It doesn't matter. The infrastructure should be able to support all of these. Multi-vendor. Okay. So design of ACI is based on the fabric as a whole, as opposed to, hey, this particular switch. Okay. So this entity called the APIC considers this as a virtual chassis. The fabric as a whole is like a virtual chassis with different components inside the chassis. That's how it perceives or visualizes this entire fabric. Okay. So it just remember, we're going to be supporting multiple vendors also. Eventually your firewalls or your load balancers, or specifically your web application firewalls, IPS, IDS, they're from different vendors. So the data center architecture should be able to support multi-vendor environments. Okay. Now, from a topology perspective, they'd use the term spine and leaf. Okay, so from a topology perspective, hardware is classified as spine and leaf. Okay, and then these are, for example, spine devices, and these are leaf devices. And you have high bandwidth. So it could be 40 gig, 100 gig, 400 gig of late. Okay. Endpoints, typically endpoints are connected to leaf. Endpoints could be physical as well as virtual. That term policy abstraction, see, that's the beauty of this. It's saying policy abstraction. Why? You never connect to a physical switch. So you can connect to it, but no config. So where do you configure all your policies? Based on application, policies are defined here. Okay, so it's got to then push the relevant command line to the different devices. So it's going to go ahead and push the relevant requirement, not even technically command line. It pushes the requirement, which is then rendered into command line on the switches. Okay. So that's why it uses the word policy abstraction. You're not jumping in or configuring each switch with its policy. Instead, you're configuring it in the APIC. The APIC has to make the decision to render it or send those policy information to the required switches. So, right there, it says it's an IP fabric. And that's no doubt, that means we're using IP communication internally. That's why the term IP fabric. We already said it's high speed. So I said, initially, emphasis was on 40 gig, now 100 gig. And Cisco already has some leaf switches which are 400 gig. Okay. So high speed, minimum of 2 spines, so at least 2. And keep in a lab environment, we could get away with 1, but then I would say you're practically not, looking at every fault tolerance scenario if you try your lab environment with 1. That being said, our lab environment for class has 1 spine. But is it scalable enough to cater to every requirement and have you test every situation, every upgrade? No. Okay, so minimum is 2. Okay. Well, leaf switches never connect to each other. It holds true even now. If you connect these two, it will shut down. Okay. They always connect to spines. Okay, the leaf switches always connect to spines. End devices. When they say end devices, that could be physical bare metal servers. It could be a virtual machine on Hyper-V or ESXi or something, virtualized environment. It could be a container. Okay, they always connect to leaf. Now, most devices connect to the leaf, except there are exceptions. You can have layer 3 devices connect to spine device, spine switches. Okay. Now, the APIC itself, that's where you define your policies. That's where you configure. Whether you configure using GUI or command line or programmability, that's totally up to you. You're going to decide that after working with the APICs. It's a minimum of 3 as a cluster. So you're going to decide that, hey, do you like the GUI? Do you like the command line? Do you want to do programmability? Because it does expose a programming interface called REST, and then you can have programming done. Okay, but all the configuration, the policy is done through here. Okay, it is not the control plane. Derek Acklincy mentioned that. These could all fail. The fabric will continue to work. Reason is it runs its own routing, switching, has its own data plane. The control plane is in the fabric, in the switches. It's not in the traffic path either. You would never have your data come in through, say, a leaf. You don't have ever a situation where traffic comes in from machine A and then transit to the APIC. Absolutely not. Not in the traffic path. APIC is always a cluster in a production environment. Again, in a lab environment, you can get away with 1, but that would not be a true test of fault tolerance for APIC. So definitely, I would suggest you have at least 3. A cluster of 3 is what Cisco needs at a minimum to support you. Okay. Every APIC server is dual homed, active, and standby until, for example, if you set up a VPC. Then, of course, that's a VPC channel, a virtual port channel. But until then, it's actually active in standby mode. Okay. And as it mentions, that's where you instantiate. That's where you define your policy. That's the policy controller. And that's where all the policies are configured. Whether, as I mentioned, whether you use the GUI or the command line or the programming interface, I don't care. Okay. Now, it's easier to build, test, support when you have a spine-leaf topology. If you need more end ports, you just add spines. You just add a few more spines when you need more endpoint ports. Add more spines. Okay. So that's what it's trying to say. Scalability is easily achieved. You need more fabric or backbone bandwidth. Just add more leaves. Add more, I misspoke. Add more leaf switches when you need more endpoint ports, and add more spine switches when you need more fabric bandwidth. So more fabric bandwidth, add spines. And add leaf switches when you need more endpoint ports. Okay. Now, according to design, connect your leaf switches to every possible spine. And that's what it is. Every possible spine. There shows you each and every one of these devices will be assigned a loopback address. Every one of them. Who assigns it? These APICs. So, example, I'm just going to pretend as if they have a loopback address which is named. I'm not writing in an IP, I'm using names to represent unique addresses. These are IP interfaces between unnumbered links. So we have a routing protocol that runs between them because these are IP devices, and that's what it says. The routing protocol, ISIS. A scalable link state routing protocol is used by Cisco to go ahead and build a routing table so that each and every one of these know how to get to each other. That means they know how to get to each and every IP address that's assigned to these fabric devices. That's the purpose. ISIS is considered the ACI underlay protocol. You really don't have a choice, by the way. You can't change it to OSPF or BGP. It is always going to initialize as ISIS. Okay, it shows you that these are IP unnumbered links. Okay. The symmetrical topology that they've shown you here, leaves connect to spines, ensures that you have any traffic coming in through here, trying to make its way to, let's say, B, server B, physically, so ingress is in here. It has another hop here, here's first hop. And then your second hop here. It's always physically 2 hops. Of course, if you were to count the ingress switch, then you would consider it 3 hops, but this is the ingress switch. So once it gets into the ingress switch, it's always physically only 2 hops. Okay. So this design allows low latency, very high bandwidth. You've got a good scalability, all of this achieved. So that's why it says now, ISIS, the underlay protocol. It's using ISIS level 1. Those of you who have worked with ISIS would be aware there's level 1 and level 2. It's all considered level 1. Okay. The IP addresses assigned to these are termed as the VTEP address. This stands for VXLAN Tunnel Endpoint. That's what they're termed, VTEP addresses. So every one of them has a VTEP address. ISIS is responsible for advertising these. Anyone ever heard this term before?
You're referring to VTEP?
Sorry?
Oh, you're referring to VTEP?
No. I circled the multicast trees. Ever heard about that before?
Oh, yes, multicast, yes.
Okay, multicast trees.
Yep, I worked with multicast.
Okay. You work with dense mode, sparse mode of multicast, or you work with anything like fabric path?
Sparse mode, dense mode, low latency feeds, and so forth.
Okay. So you haven't worked with Fabric Path. Anybody worked with Fabric Path in the past?
Nope.
I have.
Ginger, you have?
Yes.
So have you heard this term, the forwarding tag trees in Fabric Path?
No.
No? Okay, that's something that's actually done automatically in Fabric Path. So unless you dig into the lines, you may not even recognize that. Let me check what. And it's the same team that developed this product. So it is something that has improved evolved from Fabric Path. And let me see if I can pull that up. One of my Cisco Live slides might have it. Let's check. That used to be something we had learned long back in Fabric Path, and it's the same business unit which developed the Cisco ACI. So they kind of just took things that were part of Drill and Fabric Path and brought it over into the Cisco ACI environment also. If you look at this environment, there are a bunch of switches. They've called it S10, 20, 30, 40, and S100, 200, and so on. Bunch of switches connected together in Fabric Path and kind of like spanning tree protocol. And there's a reason why it's using this term root and going about this approach. Let me tell you about Fabric Path. It's a Cisco proprietary version of an industry standard protocol called Trill. Anyone heard of Trill or ever read up about it? Trill, it stands for Transparent Interconnection of Lots of Links. Okay. That's a Trill protocol. It was actually, I would say, one of the lead developers for this protocol was Radia Perlman. Anyone heard about Radia Perlman?
Yes.
Who is she?
They refer to her as the goddess of span and tree.
Exactly, the goddess of spanning trees. So don't you think it would be impossible for her to step away from the word root?
Makes sense.
So, does this look familiar now that you know it was kind of like the lead developer for this protocol called Trill was a lady who's the goddess of spanning tree, the word root, and building out a tree. In spanning tree, one of the drawbacks when Radia Perlman it was not considered a drawback then. One of the issues with spanning tree protocol is when you have multiple links which are even equidistant, it would block everything except one, right? Logically block all links except keep one in forwarding state. Spanning tree also was meant for pure layer 2, not very scalable. And Radia Perlman was looking at some sort of improvement on spanning tree. And she came up with this idea that if routing protocols, so keep in mind, switching protocol, the one we all knew was spanning tree. And around the late 90s, she started thinking over it. If routing protocols can keep all equidistant or equal links up and alive, we call it equal cost multipathing. If they can do that, why can't a switching protocol do that? So she came up with a layer 2 protocol, and then she and a few others worked with her. Trill is an IETF standard, by the way. Came up with kind of like a layer 2 protocol called Trill, which ensures it works more like routed protocols do. But in the background, Trill also uses ISIS. ISIS is used in layer 2 as well as layer 3. So Trill uses ISIS. And one of the things she had to decide on was how to handle flooded traffic. Now, what kind of traffic would you classify as flooding traffic in any given network? What causes flooding? What causes flooding? Or what type of traffic causes flooding? Thank you. I see. Go ahead, Greg.
Oh, I see that. Flooding can be done by different scenarios. Like you get flooding when the device is trying to discover something locally.
Okay.
You can also flooding, and well, it's not really flooding, routing protocol convergence. You also get a scenario of flooding when it's convergence and trying to populate its tables or database.
Okay.
The local switches will flood also when it does discovery of MAC addresses.
Okay. So Greg has given us some 3 different examples, and all of them definitely lead to flooding. And thank you, Greg. Derek has kind of given us the accurate term. Broadcast types, unknown unicast types. And then, of course, I should have just put. How do we handle that now? Okay. And that's when she kind of decided to come up with this concept that we just saw in the previous Cisco Live slide. She decided that all flooded traffic would be sent towards a root switch, and the root switch will send copies of the flooded frames, 1 copy to every other switch along the path, along the tree. The tree is the logical path. So they have this concept of selecting a root switch, and they also in Fabric path, they decided to go with the second root switch. So they actually have 2 logical trees shown here. So if I had flooding traffic coming into S800 in this top diagram, the orange color tree, tree 1, if I have some form of flooded traffic coming into S800, S800 knows its place in the tree. So what it would do is send a copy of the frame to 20, 30, 40, and towards the root. The root will send a copy towards 100 and 200. Okay, so it just ensures that every switch gets a copy of that frame. That's what we're trying to do whenever there's a flooding traffic type. Every switch should get a copy, and then the switch makes sure that it sends it out through all the required ports. So in Fabric path, also we have this calculation in the background. Even if you've never been involved in it, there is an automated method for calculating 2 trees. And unless you want to step into it and control which switch should be the root, there is no need in Fabric path to go ahead, and you may want to step into it and determine which one is the root. In some environments, people who implemented Fabric path did that because they like to have finite idea about which switch is a root when doing troubleshooting in Fabric path. So knowledge of which device is a root definitely helps, okay, when you strictly control. And this same approach is used in ACI. They have a calculation for root switch and multicast or flooding trees. And they didn't call it particularly just for multicast. I would say this is used for broadcast. By default, it's used for broadcast and multicast purposes. It's not used for the unknown unicast. So this is treated a little differently in ACI, not used for unknown unicast. It's used for broadcast and multicast. Now, the tree is built, calculated. The only catch is in ACI, only spine switches. That means only these can be root of the tree. You cannot force any leaf to become the root. Only spines. Okay. Now the other thing, this is all what ISIS does in the background for you. Okay. It ensures that it builds an ISIS routing table. So this I'm going to say builds See? Gets these trees calculated, routed at the spine, announces tunnels from every leaf to all other nodes. So here's an example. Everybody knows what a GRA tunnel is. This is kind of like what they call the VTEP tunnel. Tunnel from leaf 1 to leaf 2. Let's go ahead and build it out, and ahead of time, ISIS will build this tunnel for you. You don't need to step in and build it manually. Let's go with another tunnel from leaf 1 to leaf 3. And then let's go with another tunnel from leaf 1 to, let me take another color, leaf 4. And then again, a tunnel from leaf 1 to leaf 5. So it's all done for us. We don't need to do this. That just tells you that it is already configured for us. It does all this in the background. And that's all the responsibility of ISIS. If you really want to see the tree, you can. You want to see the ISIS routing table, you can. And it's all done for you. These trees, they have an acronym. They're called the forwarding tag, FTag trees. So if you ever see that terminology in your command line or in the GUI, and in Cisco ACI, they're always routed. The root is spine switches. They can never be on leaf. Okay. So that's all. The reason why Cisco could do that with ISI is have it do all these things is because ISI is a protocol which had TLV fields in there. Anyone heard of this term? TLV. They call the type length value fields. You basically find it in most industry standard, not all, but some. Okay. LLDP has TLV, yes. Even ISIS has TLV. So vendors can actually go ahead and put in some fields there to do their own proprietary stuff, and that's why Cisco chose ISIS. Okay. So they use these vendor TLVs to help advertise or build the tree, build the tunnel. Now, anyone heard of this protocol? It's called LISP, LISP. Anyone heard of that? And Cisco had support for LISP on their Victor, you have? Ever worked with it? Greg, you have? Okay. So go ahead, Victor.
No, unfortunately not. I only know the programming language by.
Oh, okay, got you. Not the protocol, but the programming language called LISP. Okay, got you. Greg, you have worked with LISP or ever experimented with it?
No, I know it's available through the Nexus line from Cisco.
Yes,
NXOS.
that's when it was introduced, the Nexus line. They do have, it was introduced then, it's also supported on some other hardware. It stands for Locator ID Separation Protocol. So something in Cisco ACI is derived from this protocol. And that's why they say decoupling of endpoint location and policy, decoupling. So Endpoints, right? Virtual machines or servers. That could be a bare metal server. This could be a virtual machine. That's example of a virtual machine. These are all termed as endpoints. Okay. Now, inside the fabric, for example, the spine, it knows that A is hiding behind leaf 2. So it actually keeps it somewhere in the table saying A is on leaf 2, B is on leaf 1, C is on, let's say this is leaf 6. Okay, these are endpoints. So how does the spine locate them? Based on their locator. This is the locator ID. The leaf IDs that they are sitting behind, they are connected to, those are their locators. So in Cisco ACI, this concept, identifying the endpoint's location by their locator ID, it's a very, very important concept. Okay, very important concept. That's why it says endpoints could be identified by the IP address or the MAC address, depending on the type of packet the switches have received, layer 2 or switched packets or routed packets. Switches will learn about them, put them into table, and eventually these endpoints are always identified by their locator. Okay. This locator ID would be the VTEP address. So I'm going to say that's the VTEP address of each of these switches. Okay. We already know ISIs has done this, taken care of one aspect, building this tunnel between every VTEP. Okay. So forwarding inside the fabric is usually always between the VTEPs. ISIs knows that there are all these numerous VTEPs and we have tunnels configured. So all the data plane traffic is going to come in, pass through a tunnel, make its way to another locator through these VTEP tunnels. VTEP stands for VXLAN Tunnel Endpoint. Forwarding between these VTEPs is occurring through the tunnel, and it shows you that Cisco transports it VXLAN is the encapsulation. I'm going to put a lowercase e in front. Consider it enhanced or extended. Who developed VXLAN protocol? Anyone familiar? Excuse me. It's a Cisco, VMware, and Arista. Cisco, VMware, and Arista got together and they developed this protocol and of course submitted to the IETF, and it's an IETF standard now. So there must have been a reason, right, why they developed it. It was purely to overcome layer 3 boundaries, to give the appearance of a VLAN extension, right? VXLAN stands for Virtual Extensible LAN. We want to overcome layer 3 boundaries, make sure that a VLAN extends, or give that appearance, a VLAN extending across a layer 3 or an IP boundary. Okay, that's VXLAN. Now, keep in mind, why is it called, why did they need it? Well, in the days of vMotion or clustered applications, or live migration, or DRS, or Zen motion, you're moving virtual machines around, or the system is moving virtual machines around, it should be able to move them and keep them up and active even after moving it without having to change IP addresses. So we need to give the appearance of the same VLAN. It's moving across the same VLAN. Even though it might physically go across your layer 3 boundaries, we need to give that appearance. So we had to come up with some solution for giving that appearance, and that's why Cisco, Arista, and VMware, 3 competitors, got together, put some heart and soul behind it, and came up with VXLAN. Okay. And VXLAN is an IETF standard, but these 3 vendors also ensured that there's a lot of reserved fields in there which vendors could use. And Cisco, of course, grabbed on those reserved fields, and hence it's termed EVXLAN. Means I have a frame that comes in, Ethernet frame, but once it is inside the fabric, this so-called Ethernet frame of mine is always encapsulated entirely inside the fabric with the VXLAN header. So all through the fabric, it's going as a blue towards, let's say here, for example, tunnel through the tunnel, makes its way in this format, and then when it egresses out, it gets rid of that blue header, so it sends it out as a native Ethernet frame. That's why it says transport. Your data plane traffic is always transported. Okay. Distributed reachability database. Every spine has that database which keeps track of where A, B, C, all your endpoints. Oops. Endpoints, VTEP locator. Now it's not just a spine. Eventually, even the leaves will start doing that. Okay, they have this database where they keep remote endpoints, not local, remote endpoints, and their VTEP locator. So that's why it tells you eventually every leaf will also start having this. In this protocol called Fabric Path, Cisco used to term this concept as conversational learning. Okay, Fabric Path had the same concept. Eventually, the switch tables will know where the endpoints reside and which locator. Okay, so we used to call it conversational learning. Okay, based on previous communication, these tables get populated in the leaf. So here, that's why it says it's a distributed one. It's there eventually on every leaf. That's why they call it distributed. Okay. Questions up until now? From the overview perspective. So let's take a look at how the fabric is initially discovered. The fabric does use LLDP as well as DHCP. So first and foremost, we're just going to pretend that we've just cabled them. Okay, that's the first thing. We're going to just pretend that we've just cabled them in this manner. The APIC is, and of course the switches are enabled with LLDP by default. So you would find that it's going to speak LLDP, and this switch gets discovered here. And then you register it. When you right click and register it, the API gives it an IP. APIC assigns IP addresses. That means I should have configured the APIC with some initial bootstrap information. So we're going to pretend we have these 3 APICs, we have configured them with some initial bootstrap configuration, and then hopefully the APIC hands out IP addresses to the, it hands out an IP to the first leaf. Then of course that leaf would then speak LLDP to this way, to the other spine. In this, between the 2 leaf and spine, it speaks LLDP. These 2 would get discovered here. You register them and the APIC ends out IP. And of course, this one speaks LLDP here to this leaf. You would also see that if you have initialized this APIC is also going to start speaking LLDP. So eventually they would all self-assemble. One requirement is your APICs should all be running, unless you're in the upgrade state. They must all be running the same version. Okay, the same version of firmware. There is, of course, some stock rules, strict mandated rules. APICs are only to be connected to leaves. Okay, leaves cannot connect to each other. Leaves are connecting only to spines. Should you even accidentally connect a leaf to another leaf, it will turn off the port. Then even if you intend to do VPC, if you accidentally connect 2 leaves together for your peer link, it will turn them off. So of course that means VPC in this environment does not need you to connect them. Okay. Spines can connect only to leaf switches. Spines cannot be interconnected to each other directly, not possible. Okay. Endpoints connect to leaves. That includes your bare metal, your containers, your virtual machines, your layer 4 to layer 7 devices, any other layer 2 switches. Exemption, layer 3 can connect to spine or to leaf. That's the only exemption to the rule. Layer 3 devices, that means routing devices. Okay. That is a command to check the status of your Cisco APICs. It's called, that's if you're in here, you can do ACI diag application virtualization read, and it'll tell you, it's a command line, gives you the status currently of your APICs. So this is part and parcel of that initial bootstrap configuration. When you turn on the APIC, by the way, the APIC until 4.0 had to be the specific Cisco UCS hardware. And now with 4 and later, they've started supporting it as a virtual machine on other vendor hardware. So you're going to be asked these questions anytime you turn on an APIC. A fabric name. Of course, all the APICs for the same cluster should use the same fabric name. Number of controllers, that means how many APIC controllers you're going to have in the fabric. If you read a lot about this product has actually got, I would say, a 5-bit field for controller ID. So it's actually 2 to the power of 5, which is 32. And essentially, they've not shown you 32 because Cisco has not tested all the way to 32. But that's basically why it just shows you need a minimum of 1 or up to 16 at this point. And this was version 3.2. And I believe they've increased that count now. How many are you going to have in your cluster? You said 3, right? So notice how it gives you the choice of 1 through 3. The first one should be 1, the second one you configure 2, and the third one is a 3. Give it a unique name for each controller, an IP address range, okay, an address pool for TEP addresses. So an IP address range for VTEPs to be given an address from this range. It defaults to the 10.16 address. Just make sure it does not overlap with any other routed subnets in your network. Okay. change it if it does overlap. It's quite a difficult task to change it later on. The minimum that you will be supported is a /23 subnet. Okay, so you cannot go less than that. Okay, if you ever want to modify this, you pretty much have to clean up your entire fabric and reconfigure. It's quite a difficult task, so you want to be careful about this IP address range. Similarly, even modification of what they call the infrastructure VLAN. They'll pick a VLAN that will be used for, remember initially until they get IP addresses, they're just speaking over layer 2. So this is the VLAN that is used between the APIC and the switch, or even a virtual switch for that matter. So you got to make sure this VLAN, whatever you pick, is not used for, it doesn't overlap with any other VLAN in your environment, and it should not overlap with any other reserved VLAN range of any Cisco switches or other vendor switches. Okay. Again, if you need to modify that VLAN ID, you pretty much have to wipe out your fabric and modify it. So quite a complex approach. Be careful about the VLAN ID that you pick. Something that is not going to overlap with anything else in your environment, and it should not overlap with any reserved VLANs of Cisco gear or any other vendor gear that you may connect. Keep in mind, what if I'm connecting an IBM blade switch here? I've got to make sure, and then I have a VMware, and it's going to have a virtual switch in there, and I'm going to configure some settings for the virtual switch through the ACI environment. I've got to make sure it's not part of the reserved VLAN range of IBM here. So you've got to be careful. That's why I just mentioned, make sure it's not part of a reserved VLAN on any. If it is a Cisco chassis, like a UCSFI being connected, not part of the reserved range there, or not part of any other Cisco switch that you might connect. Okay. There, it asks you for the out-of-band IP for the APIC. You're going to use this to access the APIC through its GUI. Okay. And administrator password, you've got to set that up. Okay. Once you've set this all, of course, you can access the APIC GUI through its out-of-band management IP that you just configured. Right there. You see what it does? LLDP. APIC uses LLDP to discover the directly connected switch. And then you can see how the switch is doing a request for an IP address. And the APIC gives the IP address from its DHCP pool. And that's going to be its VTEP IP. That's why it says it assigns an IP, which is a TEP address. Okay. Now, in this DHCP offer, APIC passes some boot file information. Okay, so that's why it's actually doing a HTTP GET to do the boot file. So it's actually speaking to, I remember that port used to be 7777. That's the port. Seems like Switch downloads the boot file, performs, if the boot file says that it has to do some upgrade, it's going to go ahead and do an upgrade. Upgrade of firmware, if it says that. That's why it says if necessary. Okay. And then after it's done its firmware upgrade, you can see that actually the APIC initiates it, and it's an encrypted TCP session. So that's used for intra-fabric messaging, IFM. It's a encrypted TCP session that it uses. So it's going to be using that for all its messaging to that particular switch. Notice how the APIC initiates that. It is it's not TLS encrypted from what I read in the past, and I still believe the same because I didn't verify it. It's SSL encrypted. Now, in this, we have seen that the APIC has already discovered the switches, already assigned it an IP address, and that's why it shows you this. And bullet number 6 tells you that the fabric will self-assemble. Okay. Now, 2 of your requirements here are, of course, we need the APICs to be the same version, and they should contain, that's the only way they can form a cluster. Same bootstrap. That means these previous questions that you're asked for APIC configuration should be identical on all except for controller ID and APIC name. All the other answers should be exactly the same on all the APICs in the cluster. That's the only way they can actually form a cluster, because they send in LLDP, they are part of the TLV, these do send their address vector, they send their IP, their own IP, and any other clusters that any other cluster members they're aware of. Okay, they exchange that in that field, so that's how they eventually form the cluster. Right there, it shows you that APIC servers use their internal IP to communicate with the switches and with other APIC servers. They discover that via LLDP. That's why the term address vector, address and vector, the direction. How did you find it? Okay, so APIC discovers the leaves discover the spines, APIC assigns them all an IP address, and you have a self-assembled fabric. Okay. That's a manual registration being done. When you do register, you specify a unique node ID. We'll talk about pods later when we talk about the different types of design approaches. That's when we talk about pods, POD. Okay. The node ID and a unique switch name. Okay. Now keep in mind, we have hardware, which is either leaf or spine, and now we have new hardware which you can select between both, whether they're going to be leaf or spine. The physical hardware. I always like to keep myself updated about the new hardware by looking at Cisco's, if you look at the Cisco 9000 series, I did not ask for design page. How about that? I like to keep looking at their web page rather than the documentation. And the reason being, of course, documentation gets outdated and not updated as often as I would like for it to be done. So there we are. And it'll tell you whether they are, you see, all of these, like the 9500 chassis, it says Nexus, OS, and ACI. And then you can click on the models and it shows you the models, right? It shows you the 3 chassis. And of course, similarly, if I were to pick the line cards, pick the supervisor, the line cards, let's look at the 100 gig line cards, for example. And it will tell you whether they are ACI capable. Notice ACI Leaf, ACI Spine, whether they operate with normal NXOS or only with NXOS, does not work with, you see this one? It does not, it says no and no for ACI. It can't be an ACI Spine, can't be a ACI Leaf, it can only be used for regular NXOS. So it does have the better approach to knowing hardware rather than just going with the documentation that we have pretty much in the book. So the book talks about the 9500s, which are even now only 3 modular chassis, and they're 4-slot or 8-slot or 16-slot. We also talks about the ACI 9300 switches, which can be used for 9500s. They are modular, so depending on the type of line card, right? Whether they're used for leaf or spine will depend on the line cards. Because it's a modular one. 9300, we know for sure, okay, this piece of hardware only used for leaf, or this piece of hardware used for spine. So that's 9300. And then the type of line cards that are ACI capable, they are either 97XX or 95XX, the line cards for the modular chassis. Very, very clear, these are not ACI and neither are the 9200 series. They're not ACI capable. They can only be used for standalone NXOS. When I use the term standalone NXOS, which means you can config T in the switch, you can configure the switch individually. If we choose the term ACI, that means there's no config T and you're configuring the entire range of switches or the fabric of switches through your APIC. Okay, so right there, the 9516, of course, has support for 16 line cards, the 9508 for 8 line cards, and the 9504 is for 4. We do have 2 SOUP slots, as you can see. They are half width. They are on the front, and 2 what's called system controller slots at the back. Your supervisor accepts your external clock input, your management port, your 2 USB ports, your console port, okay, and also 10, 100, and 1 gig network port. You do have different supervisor blade options. We're going to just look at that website for the supervisor options. Let me go ahead and look at the supervisors. Now, clearly the supervisor blades, they're not going to write in the column saying they're ACI or NXOS. They don't write it, okay, because it doesn't matter whether you plan to use it for ACI or for NXOS. It's the same supervisor. Ideally, production, you typically always have your redundant supervisors. The system controller cards that we just saw in that diagram. Okay, that's system controller cards. They are, sorry, not the front one. The front one's a soup, the ones that they have specifically highlighted here, system controller. They kind of help the supervisor. They step in and assist the supervisor. And some of you may have heard of the system controller cards in the past. Anyone heard of them in any other models of switches? I believe it's the Nexus 7700s, which do have a system controller card. And the purpose is actually offloading some of the functions of the supervisor. So in the past, the supervisor was responsible for entire chassis management, keeping track of power, keeping track of temperature, keeping, running diagnostics on the other line cards, running all the routing protocols, the switching protocols, and so on. So with system controller cards, what they've done is they've offloaded these chassis management tasks from the supervisor, which means the supervisor is not concerned about, hey, what's the power utilization? What should be the speed of the fan? Should we increase the speed? Temperature's gone higher, let's increase the speed. Oh, temperature's down back to normal, let's reduce the speed of the fan. So supervisor is not responsible for running the diagnostics on every line card. That is all done by the system controller. So it said, hey, supervisor only responsible for control plane, no chassis management functions. That means supervisor is responsible for running your routing protocol, switching protocol, building the tables. Okay, so that's your chassis system controller within as you may remember, inside the chassis also, they kind of use that clause technology by Charles Clause, where they have the fabric modules and they provide the connectivity through the fabric modules. So anytime traffic has to pass from one line card to another, it passes through the fabric module. That's the clause fabric design defined by Charles Clause. There may be ASICs in there. They're called the cloud scale ASICs. Okay, those are providing, let's say, 100 gig for your spine switches, with the part numbers for that would usually be ending in an fabric module E, enhanced. That's used in your modular switches to accommodate the 100 gig Ethernet spine deployment. Now, here we are looking at some of the 9300 spine switches. So I kind of remember that we have another third one now in the 9300. Let's just take a look. Maybe I misspoke, but I'm pretty sure they came out with that's the one. They introduced the 400 gig, and that's probably why I said there are a few more 9300s. Yeah, you see how it shows you that LISP is on the roadmap, but these are 400 gig, or they do have 400 gig ports, 9300 with ACI Spine. Of course, your book doesn't talk about it. It talks about the ones which are, for example, gig ones, you see, that's an ACI Spine. And you do have 100 gig, which are ACI Spine here, 9364. 9332C, and this is an ACI Leaf though, 9336. The one they have mentioned here, the 9336PQ, I'm pretty sure they stopped selling it. Okay, the 9336PQ is their first baby spine, which means the first ACI switch in spine capability in the 9300 series. It was their first baby spine. I know that they have stopped selling it, so you would be left with the one 9364 or the ones that I have shown you. So in your book, it does have like a lot of description about the 9336PQ. It's a 2RU spine and 36 ports, of course, with 40 gig QSFP capability. The 9364C is also a 2RU, and this supports up to 100 gig ports. Okay, so you have 64, 40, or 100 gig capable. They are QSFP 28 ports. Okay. Leaf, the number of leaf switches have also increased drastically. You can see clearly that these are the second generation 9300 leaf switches. They've even decided not to mention the first generation ones. Okay. So these leaf switches are improved. They have the EX, the FX, and the FX2 series depending on the requirements. And they are most of them are 1RU, but you may find, I think there is one which is a 2RU. You can see the diagram of the one in the 2RU, but there is one. Here it shows you these are only leaf switches, latency of less than, in a lot of them, their latency is less than 1 microsecond. Okay. And then they can handle like, billions of packets per second. They call that the BPPS. And of course, their backbone bandwidth will be really quite high in the 3.6 terabits per second in some cases, and in some cases even higher. The EX and the FX, they are considered the cloud scale ASIC. Okay, they are the Cisco's cloud scale LSEs, they're called, and they are smaller form factor. And compared to the first generation, they had what is called merchant silicon. Merchant silicon was Broadcom silicon, and they had a larger form factor. Cisco's smaller form factor actually accommodates more transistors. Okay. And they've kind of been able to get away with just putting a single ASIC, a switch on chip ASIC, that is a lot better than the Broadcom ones. Right there it shows you the first generation. You can see the comparison. The first generation of 9300 had a separate switch on chip, and the NFE, this one was Broadcom. And this one, application leaf engine, Cisco. Okay, in the second generation, they started basically combining these, so they don't have to, you see, merchant is Broadcom, they don't really have to pay Broadcom. And this is now the cloud scale ASIC available in the Cisco 9300 EX and FX platforms. They have a much better bandwidth, higher port density support, a lot bigger buffer sizes, accommodates thus a much larger table for your endpoint information. And greatest part of it is gives us a lot more visibility, which means we get a lot more telemetry information. Every packet and line flow at every line rate you can possibly retrieve without slowing the device. It means without any negative impact on your device. Okay. There are 3 types of cloud scale ASICs that Cisco has in different hardware. The ACE 2 used to be the first one that they came out with. Then they came out with ACE 3 cloud scale ASICs, and then we got the LSEs. And that's kind of, we will be doing this lab later, so we'll just skip the discovery aspect of it and look at the policy aspect of it. So let's look at the policy aspect of it. Everything is abstracted as a policy, everything. You want a particular web server to communicate with its database server, you might have to have a policy which permits the communication. Okay. You want to apply on a port of the switch. You want to configure port channeling, maybe. You want to configure the speed, the duplex, CDP or LLDP or any of these. These would all be done through policies. Okay? So everything revolves around policy. Now, they've just given you an analogy. That term policy is really, really generic. It is, it tells you it's in broad terms, it is some requirement. Okay. In a government or an enterprise, it is some rules that are to be followed or observed. Okay. So if you break the rule, you probably get laid off or you get suspended or whatever. Okay. So they've used an analogy, no parking policy. And that's what you see in front of a store or some restaurant or something, or on highway or road or something, you see the no parking indicator or the no parking sign. And of course, the county or the restaurant or wherever this is put up expects you to go ahead and observe, follow that rule. Okay, it's a policy. And right there, it is the intent or it's the understanding of this organization that people will follow the policy, but there will be some consequences if you don't follow. So it says policies have intent or desired outcome or desired result. And there is auditing being performed and somebody being ticketed probably because they did not follow that policy. So in our ACI environment, keep in mind, all your policies are being programmed into the APIC. Okay, so all the policies like this is a symbol put up somewhere, and we hope the drivers will follow. And in a Cisco ACI environment, the policy is defined in the APIC, if you think about it. Let me just see if I have a better diagram. Configuring it here, this is where the policies are. And then we're sending those instructions to the switches. And hopefully the switches are going to comply and configure themselves. And then if they don't comply, we can see the alerts or the faults being raised. Okay, so I would say a fault is raised because it's kind of like an audit. It's saying, hey, switch, did you perform this? Can you do this? And if you don't, hey, give me an error and I'll display it as a fault. So that's basically why it shows you that we always hope for the best. I hope that these devices will follow, and if they cannot follow, we see a fault being raised. Okay. Right there, you can see the non-compliance alert. In this case, this driver would have been ticketed and hopefully it'd have to pay a fine or something, or maybe even go to court and, you know, fight or whatever, but that's basically what happens. So it's a required, an intended desire or something that's you specify in the APIC. Okay. So that's why it says it's an intended state, and we hope that the devices will follow through and apply the policy. That's called the intended state, and promise theory relies on trust that a device will apply it. Okay. And of course, report that we cannot do it. We don't have the right version. We don't have the right ASIC. It's not capable of doing what you just asked for. So here, it's actually breaking it down on the left-hand side. You can see the GUI used by the administrator to configure. This is the GUI being used by the administrator, and it's saving it into the APIC's database. And you can see the APIC will be sending instructions, you see? It sends instructions to all your devices. They're saying, will do, they make the changes, or they cannot, they raise false. Now, every policy is reusable. That means you can build a policy once. I can build an LLDP policy, and let's say a port I want to operate. It's a 1/10 port. I want to operate in 10 gig, and I wanted to do full duplex, and I want to increase the MTU size to maybe 2500. I can define all of these into one policy and apply the policy to multiple interfaces. So it is defined in a reusable format. Okay. Policies could be used to define the configuration state of logical elements, virtual elements, as well as physical elements. Okay. And of course, they can be repeatedly applied to infrastructure wherever it's needed. Some redundancy policy, cabling policy, some forwarding policy, power policy, BIOS policy, input-output policy. So a lot of things, everything is considered a policy. Now, here's an example. Access policies. They're saying these are fabric access policies. So what is an access port? Ports that face the endpoints. On your leaf switch, ports where your endpoints connect. Or your external layer 2 devices or layer 3 devices, they're all considered access ports. Then contrast them with the term fabric ports. Fabric ports connect the leaf to the spines. So now we're talking about access policies. So definitely it's facing external. This would be within the fabric, Those would be fabric policies, access policies, facing external. Maybe a layer 2 switch, maybe a layer 3 router, maybe a firewall, maybe external facing interfaces. Maybe a hypervisor machine, maybe a NAS storage device, maybe a fax. Okay, they are collectively access policies. Okay. And these I mentioned would be fabric policies. Now, where do you configure these? It says enables configuration modularly. So each of these are modular. You see, inside the access policies, every rectangle that you have, they are configured individually. Modular, modular, modular. It's just that you attach them or associate. These are all modular. It tells you that these are managed by global administrators, not per tenant. So you'll see the term tenant coming up soon under ACI constructs. Tenant is more like, for those of you who have worked with the 7K VDC, I like to kind of draw that parallel. It's a separate administrative domain. Every VDC is a separate administrative domain. Similarly, every tenant is a separate administrative domain. Now, access policies are not configured by each tenant administrator. They are by the network or the global administrator, somebody who has those rights. Okay. Well, you do need access policies for attaching any endpoints. Identify the access interface on the leaf. So that's going to be, part of that is this one, identifying the access interface, which switch, and if you want to apply it to an entire module of a modular switch, you can do that. Okay. And it also defines the encapsulation type. So somewhere in here, I'm going to be specifying the encapsulation. Okay, like for example, I probably have VLAN pool or VXLAN pool. Those are part of all the access policies. The fabric policies would be more like VPC domains. Then we have a network time protocol. These fabric switches sync up with which NTP, MP, BGP route reflectors. Because you're going to enable route reflectors in this ACI environment, and it can only be done on spines. That's all considered part of fabric policies. Okay. So these, you would see only a network admin, they call it global admin, or the network admin, somebody who has access entirely through the GUI. This is the person who can manage these policies. Okay. These are all modularly configured. They all have their own individual web page for configuration, and then they associate. You basically form the link between these. For example, in pools, you specify VLAN pool, if you need a range of VLANs, VXLAN pool, and multicast address pools also. We'll talk about this later on. This component is where you specify which particular interface, E1/5, comma, E1/12, or E1/10 through E1/20. That means it could be a range. Which interfaces am I going to apply the policies now? Okay. Module policies, that's where I'm going to specify which line card. If I want to configure an entire line card, I would do that here. Global policies, QoS, DHCP. There's something else in here called attachment entity profile. I'm going to introduce that term, talk about it later. attachment entity profile. It's like a glue between some components. Okay. Then you're also going to specify what type of device are you connecting to. Are we connecting to a switched domain? Are we connecting to a routed domain? Are we just connecting to a physical bare metal server? Those are the type of domain. And then optionally for monitoring and troubleshooting, you can specify some thresholds, how to handle any faults, how to perform diagnostics. Those are all under access policies. Okay. So if you want to apply the same settings from here, like QoS policy, the DHCP policy, all of these to a bunch of switches, you would specify some names of switches in the switch policy, not names, IDs. Okay, so it'll apply to all those switches. Now let's take a look at an example. So here we have an interface protocol policy. So you kind of go to this option called interface protocol policy. This is on the Fabric menu, and then there is access policies. You go there and find this folder where you can create these CDP policy, LLDP policy, channeling policy, link channeling, and many more settings. Okay. Then once you configure these, you group them together. So you might group, for example, maybe I want a set of switch ports to have both CDP as well as LLDP. So then I would probably put these together. That's called the policy group. Okay. So here's another one. Then in this policy, we're going to specify which ports. You see how inside the policy, there's something called profile. These are the ports, or these ports also. Here's profile number 2, which this range. So basically, I would take one of these and associate it. And then the profile is for which switches. So these are the switch IDs, the switch numbers, the node IDs that you provided. So just shows you kind of how this configuration flows. Now, your ports may need pools or like VLAN addresses or VXLAN addresses. So that's why you saw that there was a reference to what we call VLAN pools or VXLAN pools. Right there under pools, I mentioned the term. VLAN pool or VXLAN pool or multicast address pool. Okay. So you would notice that we have these flow, which is modular for configuration, and reusing these onto different interface policies or different switch policies is what the beauty of the GUI would be. Okay, you can reuse these right there. See what it says? With interface policies, you specify the particular protocol, CDP, LLDP, LACP, whatever. You specify them and their parameters. Again, under the same, you specify the port connection type, what they call group all these policies together. Group the ports with a profile. All the range of ports in what's called an interface profile. Now, in a switch policy, notice what we have. Range of switches, this node IDs, okay. A switch group, if you want. That's what the switch group would be. And you can go ahead and specify policies for the switches grouped together. You apply the interface profile with the switch profile. These are the flow of configuration. Examples of interface protocol policies. You can set up maybe 2 for link level speed. I may call it level 1, and maybe the ports are 10 gig. Then I may have another link level policy. We can call it let's call it A, let's call this B. Maybe the ports are 1 gig. So you can have 2 different policies like that. Then maybe create another one, LLDP enable. So this has NLDP. And then you may call it LLDP disable. Then you check a box in there saying disabled from an LLDP's perspective. You can do similarly, create 2 for CDP, create 2 for LACP. You can create policies in a similar manner, create it ahead of time. So you can group them into your required policy group. Policy group gathers those into a bundle. That's what it does. These could be bundled together. Okay. Any of your interface protocol policies could be bundled into a policy group. The group is linked to an interface profile. Single interface or comma separated interface names. And then this is what actually, so if I have a policy group A, okay, let's pretend we have, I'm going to erase this all first. Let's pretend we have some policies called CDP1, LLDP1, LACP1, and a few more, CDP2, LLDP2. These are just the names that you give for each policy. You can call it anything. Naming is an art, not a science. I'm not naming it in an artistic way, just giving them numbers 1, 2, and so on. And within the policy group, you may select, let's say I want, from a CDP perspective, I want CDP1 in group A. LLDP perspective, I want LLDP2. And then LACP perspective, I have the LACP1. Another thing that you specify in here is called the AEP, Attachment Entity Profile. So it's basically saying, okay, what does the AEP associate with? A layer 3 domain, or a VMware domain, or does it connect to some layer 2 switching environment? And the AEP also specifies the VLAN range, VLAN or VLAN range, part of the pool. So it's going to specify what type of connectivity you have and which encapsulation. That's all in the AEP. and AP is assigned to policy group, which is then applied to your interface profile, which is going to specify the range of interfaces. Okay. So AP is very crucial. It specifies the encapsulation resources, the VLANs or the VXLANs available for encapsulation. Okay. The three basic types of policy groups for the access ports: regular access port configuration, port channel configuration, and a VPC configuration. When you go to policy groups, you're going to be asked this as the first question. So you can see the AEP right here specifies what we call the domain. It could be layer 2 domain, it could be a layer 3 domain, it could be a VMware domain, and that's used inside a interface policy group. That's actually a collection of access protocol or interface protocol. Now, they are part of the group. Group is then assigned to the interface profile here. What's a profile contain? A range or interfaces. That's either one. And then that is associated with switch profile, which is a collection of leaf nodes. Okay, you may give the leaf nodes as the node ID. This component, AEP, it's a profile that gets applied to the interface when the entity actually attaches. So it does specify what type of encapsulation, what type of domain it's connecting to. You see what it says? Domain. Layer 2, physical server, layer 2, layer 3, VMware, the type of encapsulation, VLAN, VXLAN. Okay. And then this, I like to call it, it's the glue between the physical. Physical is this, which specifies the interface, the switches, and so forth, and the logical. The domain, the VLAN, the VXLAN, those are the logical. It's the type of glue that sits in between, a very important component called the AEP. Here's an example of how these components relate to each other. It's nothing but kind of linking between these different components. So right there, it shows you it's linked policies together. The AEP links these logical with the physical aspect. Leaf IDs are here, interface IDs, the configuration for the interfaces. That means the policy group has the, should we enable CDP, should we disable CDP, should we enable LACP, should we disable LACP. Those are all, what should the speed be for the ports? Okay. Those are all there. And AEP serves as the gluing point between the type of domain, type of connection, and the VLAN resources. Clearly a modular approach. It is mandatory for binding these. So I can have the same domain bound to a different AP, and that binds to a different profile. So that's what's showing you that you have modularity and ease of configuration. Kind of like the connection point between the physical and the logical. VPC configuration in ACI is very, very simple. It's actually, they've simplified it. Okay? In a traditional VPC, what are your requirements? What do you need to configure in a traditional VPC environment? I'm going to give a hint. You need a peer link. What else do you need? Thank you. You need a keep alive. I'm going to say keep alive is layer 3 because if you remember, keep alive are configured between IP addresses when you configure the keep alive. This is a layer 2. Well, when you configure VPC and ACI, you don't need to configure this. You don't need to configure the two switches together directly, connect them together, even if you make an attempt to shut the port down. So it's a moot point, okay? No need for VPC peer link and no need for keep alive link either. Why do you think they're talking about this? Anyone? Why do you think they have that bullet there saying switch configurations are automatically synchronized?
I'm thinking that if you could have the member ports in the VPC on different leaves, so it has to, the configuration has to be symmetrical, has to be the same. So it has to automatically be configured, or else you'd have to manually do it on the other one.
In the past, what did we do for any configurations to sync between them? Anyone remembers the config sync option?
For the NXOS?
Yes. Anyone remembers that config sync?
No, I don't. I'm not familiar with that.
No. I'm maybe you're not familiar because it didn't work as it should. It works sometimes and doesn't work for the greatest. Config sync is what we used. And some commands would work with config sync and some wouldn't. When you really need the two switches to keep their sync configured or their port settings configured in a similar manner, we use the config sync option. And here it tells you that you don't need to do that. ACI is going to take care of it. The APICs are going to take care of it. It'll automatically make sure that the configurations are synced between the two VPC peer switches. A VPC domain is called an VPC explicit protection group in this environment. Let's take a look at a Unicast forwarding scenario with VPC. It shows you how the ACI Fabric is going to forward traffic from the first bullet. This is not a VPC host. That means I'm going to say single attached non-VPC host. Okay. Now, I should remind you that once you configure VPC and they form their explicit protection group, they're going to have what these two switches adopt what's called the VPC cluster IP. What is Anycast? What's the Anycast technology?
Is it pretty much that you can actually broadcast either, I know it as a layer 3 for like doesn't matter where you are, you can actually let that be known to the network at the closest point?
Okay, kind of agree. There is a reason why DNS servers on the internet use Unicast technology. Anyone familiar with what it does is allows, they've actually configured all the root servers of DNS all throughout the world with the same IP. All the root servers have the same IP address. Okay, so any queries to root servers from any device is routed to the closest, I'm going to put the word closest in double quotes, to the closest root server. How is closest determined? By the router. Okay, your default gateway is going to determine the closest reachable root server. So this technology allows the same IP to be adopted for different services, like a rendezvous point for multicast. You can use any cast technology. That's what this is. It says these two switches, in addition to their own VTEP IP, they also have a VPC Anycast address, again assigned by the APIC. Okay, their VPC cluster IP is a Anycast address. So in this particular example, this is a single attached host sending a frame, I guess. Host 2 plans to talk to host 1. Okay. So that's the ingress switch. Of course, you get an Ethernet frame. Ethernet gets encapsulated with the VTEP header. I'm going to say VXLAN header. Source IP and destination IP. Source IP is going to be Leaf 3 as source IP. Now maybe Leaf 3 doesn't know where the destination is, so it's going to send it to a spine. That's why it shows you that it sends it to a spine. Okay, the spine technically says, well, host 1, H1 is behind, let's say the VPC cluster IP is 10.5.3.18/16. Actually shows it like that. (10.5.3.18/32, by the way, not /16. So it shows up as host 1 is on 10.5.3.18, reachable on 10.5, which is actually the VPC cluster IP. The spine looks at its ISIS table, identifies that it has multiple paths to this. Remember, this cluster is either going this way or this way, sharing the same IP. It sends it here in this example, it sends it, you can see the bullet number 3, it sends it to Leaf 2. And then of course Leaf 2 sends it to its locally attached host. Okay, with removing the VXLAN header. At this point, no VXLAN header, it stripped it off. Now they show you a response packet. Here's a response packet, host 1 happens to pick this link, the one on the left, for the response. This table does, or Leaf 1 does a table lookup. Okay. Just because, remember, once it receives it, this leaf and so-called this leaf, they're both part of the VPC. So once it got a frame, they're both going to have this saying in their table, it's going to say host 2 is on leaf 3's VTEP IP. That's part of this table. So right now, when the host sends a response back, that's a response Ethernet frame coming in. Ethernet gets encapsulated by VXLAN. VXLAN has a source and destination. Source IP is going to be, what did I have as my VPC? Destination IP, leaf 3 is VTEP. Of course, physically, it will have to tunnel through. So I'm going to pretend as if there is a tunnel created by ISIS. So physically goes through spine, which tunnels it out to leaf 3. And when it gets to leaf 3, it gets rid of this header and sends just the raw frame to the locally attached host. Okay. Now, yes, it does support faxes, but only single homed. The fax has to be single homed. Okay. And I think the 9300s used to support 16 max and 9500s used to support 32. You can have your host in active standby. You can also have your host VPC, which is fine, but the fax is single homed. That's the only topology supported. Okay. Once again, discovery is part of lab, so we'll take a look at the discovery aspect later on during lab access. Now, what are the logical constructs in this environment? The root of this management model, or it's a language actually for modeling. Let me go back here. I think I had a diagram where I said the APIC sees the entire architecture as a virtual in an earlier diagram. I actually drew that probably. Yeah, on the first page I said this is considered a virtual chassis. And in here has a model. They use a modeling language, a modeling tree, just like how SNMP uses a modeling tree. Cisco uses a modeling language in here called the Management Information Model, sometimes known as Management Information Tree. So when you're actually logging in to the GUI or the command line and you're making any configuration changes, it's actually saving the changes against this tree-like structure, which is model of this entire infrastructure. Now, the infrastructure, not only the physical components, not the physical switches and the ports, everything, the VLANs, the VXLANs, IP address ranges, everything you configure has a place in this tree. So when you're making a change, you're actually saving it in the APICs database against the model. And then the APIC sends the instruction saying, hey, I have this change, go ahead and render this change on the switch. Okay, so you got to remember that it does have a approach, a modeling tree. It's called the management information tree. The root of the tree is called the universe. Now, Cisco meant that the original intent was this product can be used for a provider environment where you have multiple customers. So each tenant is a customer. Or I would say a separate administrative domain or unit. Okay. Each ACI Fabric is a independent tree, and within the tree, it has a logical entity called a tenant. Every tenant is a separate administrative domain. The intent, this product was supposed to be used more in a provider environment where it caters to multiple customers. So each customer would need their own administrative unit. It's like a container. Each tenant container will then hold the policies that each tenant administrator manages. So within the tenant, you have what is called the layer 3 logical separator. Used to be called context. Now, of course, we know it more as the VRF. Okay. So it's a unit for administrative purposes and for separation or logical separation of traffic. That's what it is, a unit which is isolated in itself from other tenants. Within the tenant, this is your layer 3 domain, the layer 3 segmentation, the VRF, or what they used to call a private network at one point, and before that they called it the context. But we all know, everybody familiar with the term VRF, right? Anyone who's not familiar with VRF? Okay, so everybody's familiar. Now, in a provider environment, a tenant is a customer. But in an enterprise environment, what would you do? Would you configure multiple tenants for every department? Absolutely not. You may just have 2. There are 3 by default, and then you may just create 2. You may create a production one, and maybe you will have a dev test one. That's it in an enterprise environment. Okay. In a service provider environment, it would be for each customer. Now, that's a tenant. Within the tenant, we have the layer 3 separator. Can you share between tenants? Yes. Can you reuse the IP space? Yes. Okay. 3 that are there by default. I mentioned that there are 3 by default. You cannot delete them, or you can configure them, but we have, let me look at the response that, it's just checking on your codes. The 3 that there are by default, they are known as common, infrastructure, they call infra tenant, management. And by their names, this is a special tenant who provides, or anything you configure in here is available to other tenants. It's mainly for global reusability, which means anything in the common tenant, that's the core idea behind the common tenant. Like you have a DNS server that is to be used by all tenants, or an NTP server that's to be used by all tenants. Okay. So there shows you the description of common. Infrastructure tenant. It's all for my, remember I said after they get an IP address, they do infrastructure messaging, IFM between the APIC and the switch. So for all internal fabric communications, creating the tunnels, pushing the policies, that they use the infrastructure. Any switch to switch communication also goes along the infrastructure tenant. Okay. And then of course the management tenant, all the methods of configuring your management access. The access policies for configuring management. Out of band or in band management, who can manage who, which IP address ranges are allowed to connect, they're all done under the management tenant. Those are the three. Then of course you would build your own production one and maybe a dev test one. In a common scenario like an enterprise, that's the only tool you would add. You don't need numerous others. VRFs, of course, your layer 3 segregator. It is nothing but a separate IP space. You cannot have a VRF speak to another VRF if they're using the same IP space, but you can leak IP address ranges if they are different in the VRFs. Okay? So when ACI was released, they did not term the VRF as VRF, they called it context. Then after context, they started terming it private networks, and now they've decided, oh, we're going to go ahead and use the term VRF. Okay, so it's a layer 3 segregator. That's what a VRF would be. Then right there, within the tenant, your VRF. You definitely have to have one. It's not a can, you have to have one. Okay. Can you have multiple? Yes. Depends on how you would like to segregate your layer 3. How many do you have currently? Use the same. Okay. Now, right there, provide separate IP space. You can allow them to communicate between VRFs if you need to. As long as they have a different IP space, you can. If you want to, you can configure for between VRFs, you can leak or have the IP space shared. Okay. Then how do they communicate within the VRF? Now, the first and foremost, a core requirement is you've got to define what's called an application profile within the tenant. So what's a profile? A profile is a collection of what's called endpoint groups. That would be if it's a multi-tier application, every tier, maybe a web EPG, application servers, endpoint grouping, database servers, endpoint groups. Okay, so these three together make up the components of this multi-tier app. They use different colors in this picture, the blue, the red, and the orange. Between these, by default, okay, between these, no communication allowed by default. Now, that's the default. So you really have to have what they call a policy, or they term it as a contract, in order to allow these to communicate. Okay, so remember, I'm using that emphasis on that word default. Communication between EPGs is denied by default. Now, could I have said, no, I would like them to communicate by default? It's possible. There is an option on the VRF. When you build your VRF, what did they call it? I can't see the name, but they called it something. And there's an option for you to pick enforced or unenforced. Right now, the default setting is enforced. Enforced means by default, we would have to have a contract to allow traffic to communicate. If you had it unenforced, then of course the EPG could communicate without the contract. Now, sometimes if you're trying to figure out if it's a problem with the contract or not, what you could do is you can change this button, just put it to unenforced and see. That means you can disable the policy control and see if they can communicate. If they can, that means you have an invalid contract. Okay, at least it narrows down, it points you in the right direction. Okay. And then, of course, once you go ahead and fix your contract, go ahead and change the switch back to enforced. Okay. Also be careful, if you do it in production, it's going to disrupt your production traffic, so be a little careful about using that enforced and unenforced during production hours. Then you may notice they probably have not used the term there, but here, you see, they use the term bridge domain. Nowhere have they used the term VLANs. They use the term bridge domains. They called it the layer 2 forwarding construct within a fabric. Okay, so if I have this fabric and it's all IP links between these, leaf and spine. This is my fabric. What did I say is the encapsulation within the fabric? What's the encapsulation type used for data frames, Ethernet frames, coming into the fabric? Thank you, Derek. VXLAN. First and foremost, I've already said this is an IP fabric. So would you classify it as layer 2 or layer 3? The fabric is layer 2 or layer 3? Thank you, Gregory. That's a layer 3 fabric. Okay. Now, if it was a layer 2, suppose this was a layer 2. What would be my flood boundary? I'm going to use this question. Flood boundary. That means floods are contained where? What would be my flood boundary? Suppose it was layer 2. Every time you think about flooded traffic, right, broadcast traffic, does it automatically cross a layer 3 device? Broadcast traffic, where is it contained in a traditional network? What is your flood boundary? Thank you, Derek. VLAN. Suppose this was layer 2, my flood boundary would have been the VLAN. Agreed? But I don't have a layer 2 fabric, I have a layer 3 fabric. VXLAN is all about layer 3. So now Cisco, Arista, and VMware came up with a new flood boundary. VXLAN is your flood boundary. Sorry, not VXLAN, the new term I should introduced. Not the entire VXLAN, sorry. The term I had to put in was bridge domain. So you're going to create that, you're going to specify the flood boundary name, and then you're going to specify which IP subnets would you like to flood into. Okay, now keep in mind, your data traffic is already encapsulated in VXLAN header. So you're just saying, hey, send it to subnet 10.3.1 and 10.3.2. So a bridge domain, if you notice, it's one or more IP subnets. It's your flood boundary in VXLAN environments. Okay, it's a container for subnets. Because that whole fabric is now all IP based. It's not using VLAN encapsulations. It's all VXLAN, which is IP based. Okay. Exists in your VRF. You can have multiple bridge domains within the VRF. Okay. And here, it kind of shows you the bridge domain's name is something there. And by the way, every bridge domain also has its own multicast address. This is your flooding domain. Okay. And right there, it says, how should we handle? Remember, flooding was B, U, and M. This and this, I said we do use the multicast forwarding trees. Unknown unicast. By default, in ACI, doesn't use the tree. How does it handle it? It's called the hardware proxy. Hardware proxy is a concept where the leaf switch says, hey, if I don't know, I'm going to ask the spine. That means all others, my spine is the default gateway. If I don't know where a host resides, okay, if I don't know where the host resides, I'm going to just forward it to a proxy device called the spine. That's the setting on the bridge domain saying unknown unicast should be sent to a hardware proxy. Okay. There's also some other settings here. It'll determine whether these subnets get advertised to any other layer 3 links that you configure for the bridge domain. It's going to go ahead and let you configure those settings, advertise externally. If you want to share this information between VRFs. Now, this key, send the packet hardware proxy. That means ask the spine, because the spine is kind of like Mr. Know It All. Now, with this configuration, if the spine doesn't know where a host resides, it doesn't know the locator, the packet is dropped. The advantage of hardware proxy is technically for unknown unicast. This is versus a traditional network. For unknown unicast, no flooding occurs in your fabric. Disadvantage is I'm hoping my spine, at least my spine, knows about every endpoint and the capacity of the spine. Okay, capacity of the spine varies based on hardware. 9516, for example, with the cloud ACIC fabric modules or cloud scale, it can hold up to 1.2 million host entries in its table. Now you could change it to flood mode. That means flood it to the 2 or 1 subnet defined in the bridge domain. You flood the packets to the bridge domain, the entire bridge domain. And you may even use it when you are probably extending a bridge domain to an existing external layer 2 network. You might decide to just flood it. Okay. You also see how ARP flooding is not enabled. By default, it doesn't do ARP flooding. Okay. So I'm going to pretend as if we have a fabric. We'll just go back to one of those diagrams so I can draw out how ARP is not flooded. Instead, it does what's called maybe a directed I'll use the term directed unicast, but technically not actually a unicast, but I'll use that term. Let's pretend there is, maybe not, this one is VPC description, maybe here. I'll pretend there is a machine A connected to leaf 2. We'll just call this leaf 2, by the way. Machine B also connected to leaf 2. And C is connected to leaf 5. A has done an ARP. Okay, A has done an ARP for C. And at some point in leaf 2, there is an entry in the table which says, this is a table, not the ARP table. I'm going to very specifically call it the global station table. That means remotely connected endpoints. I'm going to say that it, according to leaf 2, C is on leaf 5 VTEP IP. Okay, now remember, ARP has 2 components. There's an ARP request and there's an ARP response. Which among these 2 are broadcasts, and are they both broadcasts, request and response? Anyone? An ARP request, is it a broadcast, a multicast, or a unicast? An ARP request. No one remembers that? Thank you. Derek and Gregory have said ARP request is a broadcast. ARP response is a broadcast, unicast, multicast. Thank you, Gregory. ARP response is a uni. So I'm going to say this is broad, not multi. I don't know why I'm. And this is uni. So A has previously done an ARP for C. I've not gone through the details, and it got a response and it stored it in the station table because of a previous communication. A C is behind this locator L5. Now B does an ARP for C. So remember, incoming is an Ethernet broadcast, which means send to all devices in a VLAN or in an IP subnet. Technically, that's what an Ethernet broadcast is. But in the fabric, we never have those packets go in as raw Ethernet. The fabric encapsulates now, the first thing the Leaf 2 is going to do, because it's ARP, it actually snoops the packet. It identifies it as an Ethernet type ARP. It looks at it, it's an ARP request. It sees that it is for C. It says, well, I have a broadcast request for C, but here's something I already have in my table. C is on L5. So this ARP broadcast, word emphasis broadcast. What's the destination address for a broadcast in Ethernet? Anyone? The MAC address? The MAC address for an Ethernet broadcast? Would you agree? It's all Ethernet destination address. Bunch of Fs, 12 Fs. Okay. So destination is a broadcast. There is a flag in there for ARP broadcast saying it is an ARP request, not a response. So the Leaf 2 looks up, it finds C, and it says, well, I'm going to go ahead and put a VXLAN header. So source IP, Leaf 2. Wow, I don't have to broadcast it and send it to the multicast tree. Instead, destination IP is going to be Leaf 5. Okay, observe within the fabric, it's actually sending it to only one switch. That means it changed the broadcast into a directed unicast. In VXLAN, it's only going to go ahead only to this switch. The default setting, if you recollect, on my bridge domain doesn't have ARP flooding enabled by default, and you would leave it as such unless you were connecting or extending this bridge domain to a traditional environment. Okay, so you may see how it tells you that ARP flooding is disabled by default. So technically, within the ACI, it's transported as an IP packet because VXLAN, of course, has got all the new IP headers. It will make use of the multiple paths between your switches and will send it faster. It tells you that you have the option to change these based on what you're connecting your environment to. Now, we'll look at the other switches gradually, those other fields gradually. Let's get back, discuss this topic, which is, of course, about the term hardware proxy. Now, I did use this vocabulary before lunch. I said the spine, I like to term it as the Mr. Know-It-All, because it is supposed to eventually have knowledge about where each host resides. That table is termed as the proxy table of the spine. It's termed like that. There is a reason why it's termed like that. I'm going to go ahead and tell you just about why it's termed. But this table is known as the hardware proxy table. So essentially, that's the reason why the flooding of unknown unicast is not enabled, purely because we have this spine which knows about everybody. And let's see what happens. So example, all of these leaf switches, L1 through L6, spine 1 through spine 4. The leaf switches have a table which is called local station table. Local means locally connected access devices. So E, A, F, they are all locally connected devices. So there's a local station table and there is a global station table on leaf switches. These are both on leaves. On the spine switches, I'm just going to go and right there. It's called the spine proxy table. So I'll just call the hardware table. There's so many different terms, okay? But spine proxy is quite a term that's used very often. So E, A, F, all these are locally connected on the leaf 1. So if I were to just write the leaf local station table of leaf 1, it will have E, A, and F. E, for example, on port E1/3, suppose that's 1/3. So local station will have locally attached or locally learned frames. Locally learned. Locally learned means those which are learned through access ports. The frames, their information, and the port number. So that's the relevant port number example, port number. A global station table has an example would be B. That's B. It's learned through the fabric. Remember, these are fabric ports. These are called the fabric ports. So global station table is entries, MAC addresses or IP addresses that are learned through the fabric ports. And it essentially will associate with the locator. So essentially B is on locator L4. That's the L4 VTEP IP. One of the entries in here is kind of like all others. It's like a wildcard. Send to the spine proxy. And I'm going to write spine Unicast address. So what we have is all these spines. They all have their individual IPs given to them. but they also have a common Unicast VTEP. So in the global station table, there's an entry saying all others send it to the spine Unicast. It means, hey, just speak to any spine. Okay. Now, the spine table, L1 learns about, let's pretend, L1's local station table learns about a E1/5. There's a frame coming in, so L1 learns about it. It says A is on E1/5. It sends the update to the spines. We have a proprietary protocol in use here. It's called Council of Oracles Protocol. So my leaf sends the update to the VTEP of the spine. Now keep in mind, from a layer 3 perspective, it is sending it to the Unicast address of the spine. That would be a common address. Let me ask you something. If you have in a network, let me draw it differently. Wrong diagram. I have a device which has connections to from a layer 2 perspective. Now I don't want to draw 3 devices, but I'm just going to pretend as if there are 2 devices. If these are both considered same logical entity, like a VPC, or like a MEC, which of these physical links, if switch 1 wants to send traffic to either of these 2, which of these physical links is it going to pick? If I had a VPC. If this was a question of VPC, a switch has a VPC to 2 other switches, which of the physical links will it pick to forward a frame? How does it could be either, but depends on the hash.
Is it like the root of the VLAN that it's sending on, whichever one's the root?
Technically, no. When it's a VPC, that's considered equivalent, right? Both links are the same. So Felipe had the answer. It is based on the hash. And typically, it is based on the 5-tuple or 5-tuple hash. VPC always goes by that decision. Okay. Source IP, destination IP, source MAC, destination MAC, and protocol. That's how VPC makes the decision. That's the hashing technology used by VPC. Now, in the ACI environment, if you think about it, these all have a common Unicast address. So this is kind of like a port channel or a virtual port channel, and it's going to hash it onto one of these physical links. So this protocol that I just wrote about here, what is it doing? A is on 1/5. So local station table has an entry that A is on E1/5. While using this protocol, it's supposed to send it to the spine, so it hashes it. Maybe it sends it on this one. So this spine will have an entry saying A is hiding behind L1 locator. The spine informs the other spines also using QoP. So all of them are going to have this entry. A is behind L1. Now here is something that you have to know. any changes to local station table on leaf switches triggers a QoP update to the spine. So in other words, the entry gets removed from the table, updates the spine. New entry is added into the table, updates the spine. So that eventually the spine is going to know about everybody that sends frames this way. That is called the proxy table. So by default, we have the Unicast, unknown unicast flooding is turned off purely because of the fact that the leaf switches will resort to accessing the spine, and the spine will know about pretty much everybody. The default behavior, if the spine doesn't know, let the packet be dropped. That's the default behavior. Okay. So within the tenant, we have the VRF, one or more. Notice they're just putting it all together. Within the tenant, we have one or more VRFs. And within the VRFs, we have the layer 2 flooding domain. This is bridge domains. And a bridge domain may comprise one or more subnets. Okay. So if I were to summarize it, it's like in a traditional network, there used to be MAC address table, routing information base, ARP table. In ACI, it's kind of replaced the MAC address table. I'm not going to say it completely got rid of the ARP table. It does do an ARP, okay? So just, I don't want to say it completely got rid of ARP, but the ARP table is really not needed because it utilizes the endpoint table. The endpoint table serves a whole lot of purpose. Okay. And of course, within that, we have what's called the groups of endpoints. So now this is where the skill of the design is, or the skill of the designer comes into question. The product itself is named application-centric. Okay, application-centric infrastructure. So if you think about it, it says the product revolves around multi-tier apps. Common is 3-tier. Okay, so essentially, as a person who's designing the network, you would be best served if you know how to design these applications requirements. You should know the tiers and how they're going to communicate. Every tier is typically a EPG. An EPG is servicing an application tier. Collection of endpoints. What's an endpoint? Typically servers. In a data center, there would be servers. Collection of endpoints that need to be treated in a similar manner, similar policies. That's what we call the endpoint group. The collection of endpoints which require a similar policy is known as an endpoint group. The logical grouping of hosts or servers that need to be treated in a similar manner. They probably have the same permits being allowed to communicate to them and from them. They need the same QoS policy. Every EPG has to be associated with a flooding domain. That's why it says exists within the bridge domain. Within the EPG, and this is by default. Intra-EPG is unrestricted unless you change the configuration of the EPG. You can actually go ahead and say, we want isolation within the EPG. That's possible, okay? But by default, intra is allowed, and inter is controlled by contracts, or the term they've been using, policies. Okay. I would say collection of endpoints or an application tier. Every EPG exists in one bridge domain only. Within the EPG, unlimited communication between EPGs. It is controlled by contracts. So each EPG will be identified, or traffic, when it's allocated, it will be identified by a header, maybe like a VLAN header or an NVGRE header or a VXLAN header. Okay. Now the endpoints themselves will be grouped within the EPG. There shows you they could be virtual machines, they could be bare metals, it could be mainframes, it could be your layer 4 to layer 7 devices, storage devices, even your switches and routers will then belong to EPGs. Okay. So that shows you, example, EPGs are grouped within an application profile. A profile is a bunch of EPGs, like in this example, 3 EPGs grouped together as part of a profile or as part of one 3-tier app. Okay, it's a container for holding all those different EPGs with all their contracts or policies. A contract will have permit, deny. It will have the QoS policies, maybe layer 4 to layer 7 devices. They call it the service graph. Firewalls, load balancers, and so forth. Okay, that's what an application profile is. It's like a container for multiple groupings put together, or multiple components, multiple tiers of your application. They are categorized as EPGs. Physical servers being added to an EPG is fairly simple. Okay, when you're associating physical servers to an EPG, they're called bare metal servers. You just go ahead and create what's called a static binding, a static path. You say, well, this port or this whole blade, okay, this port is going to be in this EPG and this is the VLAN. That's pretty much how you go ahead and add physical servers. You just specify the port that the server is connecting to, the VLAN that it should be using, and go ahead and associate it with the EPG. So in this example, they're showing you how you're actually, you notice when they're creating the EPG, by the way, this is an example of EPG being created. They gave it a name, and then there's a link here saying statically link with leaves or paths. So you can actually go ahead and specify a particular blade on a leaf switch, or the whole leaf switch, or a certain port on the leaf switch is to be associated as part of this application EPG. That's one approach to statically link something. So you're basically giving the EPG a name. You can give it an alias. Notice by default it says intra-EPG isolation is unenforced. That means within the EPG, you have unlimited communication. We don't have a restriction. Okay, we are going to see what's called a preferred group member. you can actually group certain EPGs together as belonging to a group, so then they can talk to each other without a contract. Okay, that's an option. Now, in this case, we are not adding the EPG to the preferred group member. That's the default. It says exclude. Okay. Then is flooding enabled for that particular encapsulation? If you use a VLAN encapsulation, is flooding enabled? No, it is not enabled by default. Okay. The other fields, we will, if you're using it with VMware, you'd have to select this, and then this is the bridge domain with the EPGs configured with. We can configure a monitoring policy and a trust policy. We'll look at the monitoring policy and the trust policy a bit later after we discuss this. So by the way, when you click next, it tells you to pick your leaf or path. And here is an example where they have selected port Ethernet 1/10 on node 101. That means it's a leaf switch 101. And it's going to use encapsulation of 701 for the VLAN. You do get the option to say whether you want tagged traffic, untagged traffic, that means no VLAN ID, or just an 802.1p tag. You can actually go ahead and specify. When you click on add here, it asks you some of these questions. Now, should you have the multiple EPGs, you definitely need to provide contracts. Contracts are the sole entity, or I'm going to use the word construct in ACI, which enables EPGs which are disallowed from communication to actually communicate. This is the sole construct in ACI. I like to term this as the white list, because without this, they cannot talk. With this, we're specifying the permits. And this is given that everything is at its defaults. Okay. So EPGs, contracts that allow the communication, they are all collectively termed as the application network profile. The EPGs, that's the tiers of the application, along with all the contracts in there. Examples, contracts can be reused. Okay, you see an example of the contract C here. There is a EPG called management. That means a range of IPs, maybe or certain devices which can manage the web servers, the application servers, and database servers. They're using the same contract to be able to manage here, as well as manage there. Contracts are reusable. They contain your permits. Okay, that's why it says reusable for multiple EPGs. And EPGs can inherit multiple contracts. So what does a contract do? Permits. It specifies which protocol, which ports are allowed to be used between two tiers of the application. Now, contracts have this, when you build a contract, like I'm going to draw an analogy, okay? In the past, when you're on a router or a switch, you would create an access list, and then you apply to an interface, let's say an interface. To make it easy, of course, you can use access list for several reasons, but let's just apply to an interface. Then you give a direction. Okay, now contracts with all its permits and protocols and port numbers apply to EPGs, and then you specify. Instead of direction, you've got to specify when you apply it, whether it's a consumer, or a provider. Like when you specify direction, you can only do an in or an out. So when you apply the contracts to the EPGs, you only have these choices, consumer or provider. Now you may wonder where Cisco got these terms from. These are terminology used by application developers. So they kind of grabbed those terminology because the original intent was app developers should be able to go ahead and roll out their network requirements whenever they need to test an application, roll it out per their need. Just, click a few buttons in the GUI and then specify what the application is going to do, and then the network should automatically design itself or configure the switches based on the need. That's why the product is called ACI. Okay, that's why they've taken those terms from application development, consumer and provider. Okay, so typically, EPG can only communicate to another if they have what's called a provider and consumer relationship. A provider and consumer relationship. For example, notice this is the provider. You see how it says provides. This is probably external clients. It's a different EPG. And it's consuming. You see the word? It says consumes. So there's always two parts to the contract. One is a EPG that's providing, the other is an EPG that's consuming. Now, for those of us who are from networking for many years, I did some programming long time ago, and I even totally forgot when I started working with this product. I remembered, oh yeah, it sounds familiar to me. Why would they use the word? We have used the terms client server for protocols. Okay, we've heard of this. Okay, client server protocol. So HTTP, for example, server side is 80 or 8080 or something. What's the client side? What's the port number on the client end? Okay, thank you, Gregory. He said random. I'm going to say ephemeral or any port higher than 1024. I'm going to go ahead and use all those. Random. Something higher than 1024, most likely, unless it's a reserved port. Okay, so we use the term client, maybe random port, communicating to the server. Now I'm going to say what the application developer would use instead of what I said. They would say the server, let's call it Web A. Web A, if I were an application developer, the sentence would be more accurate. They would say Web A provides, understand the word, provides port 80. Client B consumes the port 80 services. That's how an application developer would talk about it. They don't typically just write the word client server. They would say Web A provides port 80, client B, for example, consumes the port 80 services, whatever is being offered by Web A. So I'm trying to highlight the word consumes and provides so you can understand what this means. Okay, so in a contract, you have filters These are the actual commits or denies. It specifies the protocol, the port number, and so on. You may have QoS policies. I would actually maybe even rewrite this a little bit. A contract actually has a subject, which is gluing the filter. You'll see why they have this concept called subject. That glues the filters. Then you have your QoS policies and probably maybe service graph, layer 4 to layer 7 service graphs. So these are the ones which actually do the permits or the denies. Okay, so a filter is typically specifying a source port and destination port. It's usually used for a direction, a particular direction. Okay, this is most often what we use, bidirectional. The initiating side is typically a client. They consume. So a web browser initiates a request to a server. Typically, the client initiates the communication. Okay. So in this particular example, it shows you the client initiates, it's consuming, the services are provided by the web server. So it initiates. Once somebody puts in some, let's say this is an Amazon web server, you're putting in a request or you're searching for something, and then you decide to purchase it. When you click on purchase, buy, add to cart, your application server kicks in. And then it will prompt, it'll go ahead and tell the web server to ask you for your credit card and billing address and so on. So once you click, they put all that information. This would probably talk to your go through your PCI and verify your card information. And then once the purchase is made, it saves it into the database. So you can track your order information later on. So typically, most applications nowadays are 3-tier. So here they break down for you contract. Contract has a subject which glues the filters. It's a group of filters. Okay. This itself is the permit or deny. Okay. Or even mark the traffic. And you build a contract. I'll show you the subject later on. When you get to lab, we'll see the screen, the purpose of the subject. Why? I can build independent filter and reuse those filters in different contracts by using different subjects. Okay. So eventually, once you build a relationship between your EPGs, like in this case, they have a web EPG, an app EPG, and a database EPG. When you apply the contract, for example, this contract, okay, it's basically saying web is a consumer, app is a provider. How do I know it's basically saying that? Based on the arrows. Okay, that means it's saying that this server is providing the server side services, and this client, the web server, this is a client of app EPG because it's consuming. And how do I know that? The arrow. Okay. So you can actually determine based on once you get there's a graphical application profile diagram, it'll tell you how you have configured, who's the provider, who's the consumer. So that's what it's showing you. the contracts when you have eventually configured. And by the way, you can click on these contracts. It'll show you the filters or QoS or any contracts when you build them. When you create them, they're independent. They are not applied to any EPG. So when you create them, you get to choose whether they are global in nature. That means you can use it in any tenant, tenant only, okay, or for a particular VRF only. You can actually go ahead and limit the scope, the availability of the contract by choosing that option when you build the contract. By default, contracts are tenant nature. That means they are actually available for you to use anywhere within that tenant. Okay. The subjects, the group of filters put together. It's kind of the glue. The subject itself, you cannot create a separate subject in itself. It's needed when you're assigning contracts into a. So this probably is contract A. And you're assigning some filters to the contract A. You actually use a subject. Combination of a filter, the action, and a label. I'll talk about label. It's used for what is called an implicit trust. It just specifies what is allowed between the consumer and the provider. Right there, it shows you a filter is purely a protocol and port numbers. That's it. Protocol, port numbers, permit, deny, log. I should say the VZNA was probably added in 1.2 version. Okay. Now, in ACI, by default, now keep in mind I'm emphasizing on this term, they can change the defaults quite a lot. But by default, an APG can only communicate to another APG based on contracts. Okay, so the contract would decide whether it's used as a provider, consumer, or both. It is this object called VZNE is actually a way to reduce the consumption of your TCAM on your actual switches. When you want a contract between one EPG and all the others in that VRF. You want a contract between an EPG and all the other EPGs. Okay. Now either, here's what you can do. Suppose I have EPG 5 and I want a contract between the same contract between EPG1 and EPG5. I would do that specifically. Maybe this is the consumer, this is the provider. So I do it once. Then I would have to do the relationship between these two. The contract, this is the consumer, this is the provider. Then I have to do this. So I've got to do this 4 times. Okay. However, Cisco does provide a predefined option called all others. That means I can say EPG5 and VZNE. A convenient way. And the good thing is, not only does it reduce administrative nightmare, it also reduces, if I had done it 4 times, it would have downloaded 4 times into my TCAM. I don't need that. If it's the word VZNE, it downloads, or the APIC pushes it once into the switch TCAM. So that's Why? This is a very convenient method if you really need to use the policy between all other EPGs of the VRF and a specific EPG. You would be better served by using this option called VZ-Any. Okay. First example, it shows you use cases. VZ-Any is the consumer and the other one is the provider. Okay, so this is a particular, let's say EPG5 is the provider, and this would be all others. Okay. In the second scenario, you can see that all others are providers. Okay, all others, maybe this is EPG1, it's the consumer, and all the others are providing. Okay. And the third scenario is like pretty much, hey, any to any, it's basically that. If you look at what the third scenario is. So we will be looking at configuring those logical constructs as a part of our lab later. And that would be the discussion there. And now let's look at the header. Question, VLAN is an encapsulation protocol. IPsec is a security encapsulation. MPLS is for transport, MPLS header. Which layer would you classify these as? Okay, VLAN is, I assume, layer 2. Ginger mentioned. What about IPsec and okay, Felipe said IPsec is layer 3. And MPLS, Victor, that's the right answer. 2.5 is what they say, right? Because it's neither layer 2 and neither does it cover layer 3, so it's in between the two. It doesn't encapsulate your IP address if you think about it, right? It's caught in between, so that's why they call it the between the layer 2, layer 3. Shells got that. It is kind of like the 2.5. It doesn't encapsulate over your IP, but it encapsulates over your layer 2 header or between the layer 2 and layer 3. Now the next question is, where would I classify VXLAN as? Which layer should I classify it under? Anyone knows? Or can you even tell me by looking at this diagram? Ginger said 4, or maybe she's asking me. Felipe is saying 3. Technically, if I were to look at it, it says it's within UDP. Now, what would you classify anything that runs over UDP? Which layer? Anything that runs over UDP. What is TFTP as an example? What layer, what protocol, what do you classify it as? Yeah, probably 4 and above, or something higher than 4, right? If technically, if you were to use the OSI model considers this as layer 4. But if you were to go with the TCP model, TCP considers this as layer 3. Okay, TCP/IP model considers UDP and TCP as their layer 3, and then everything about that is their application level, right? So I would be a little like, I'm like a little lost. Where should I want, what do I want to classify? Something that is higher than, look at this. It says it is actually a UDP based. So many of you said 4 and higher or something, 4-ish. Okay, that would be answer. Okay, so it takes your entire Ethernet frame. That's your original data frame coming in. Minus, I'm going to say minus any VXLAN or VLAN or NVGRE encapsulation. So this is my entire Ethernet frame, which could be TCP or UDP based application, minus any encapsulation like VLAN or VXLAN or NVGRE. Any of those, it's going to strip that out. It accepts it and it encapsulates it into VXLAN. So we do have original, we have new, we do have original Ethernet header, we have new Ethernet header, we have original protocol, TCP or UDP, we have UDP. So the new IP header will always be VTEP IPs. The source and destination will be VTEP IPs. The original header is always still maintained within the frame. Okay. Now keep in mind, we call it a virtual extensible LAN. So we always think about it as if it's a layer 2 encapsulation. We always presume it's a layer 2 encapsulation, but ideally I feel that is probably misleading many of us because we think about it as if it is a Ethernet header. It's actually taking your original frame as is, minus any encapsulations, and then putting it into a VXLAN header, which then encapsulates into UDP, another set of IP addresses, and then your outer Ethernet header. So approximately another 50 bytes of header is added, an additional 50 bytes. Okay. Now, within the VXLAN header, of course, is the field for the VXLAN network ID, the VNID. Okay. Which is kind of like identifying your VXLAN number, like just like how VLANs have VLAN ID for identifying the VLAN number. Similarly, VXLANs have VXLAN network ID to identify the VNID. It's a 24-bit field, so I'm talking about 2 to the power of 24 versus like 16 million odd addresses versus a 12-bit field of VLAN, which was only 4,096 segments. Okay. Now, you see a bunch of fields reserved. Cisco actually starts using a bunch of these fields. There's also originally in the VXLAN, notice how they said Cisco ACI VXLAN header. They did not say VXLAN. Even this field is originally reserved. So Cisco actually goes ahead and uses this field to put in what's called the source EPG, the EPG of the originating endpoint, source EPG. We have, yeah, right there, flags. If we have a type of load balancing, DRE, discount, it's called discount, not discount, discarding rate eliminator. That's what it is. It's not discount, it's actually wrong there. Shows you whether that certain type of load balancing is in use. Notice this bit is going to say, hey, destination TEP should not learn the source step to inner binding, should not learn it. It has encountered some forwarding exception. It's kind of like, we'll talk about bounds and fast rerouting later. Whether the source has already applied the permits, it's already decided on it. Okay. Whether the destination policy has already been applied. The load balancing bit is to set where all the extent of the load balancing, that's what the bit there is, DRE. And then of course the MCAST is how should the multicast range, should it be routed or should it bridge? We're going to see some of these forwarding exceptions in examples. So just be aware that there are these fields which are pertinent to EVXLAN. That's why they're being used. Okay. Source group is a very important field. Source EPG. Very important to know where the origination, which EPG the traffic originated from. Now, that's talking about the VTEP. Remember, the VTEP, VXLAN uses these switches. They're called the VTEPs. Endpoints are typically located by the VTEP IP in the global station table or in the proxy table. Endpoints are identified by their VTEP IP. All forwarding inside the fabric is based on VTEP IP. So, who does the VXLAN encapsulation, the VTEPs? Who does the de-encapsulation, the VTEP? So these devices are going to go ahead and do the VXLAN header and also strip that off at the other end. Now, the leaf VTEPs, they have two interfaces if you look carefully, leaf VTEPs. That's the local or access ports. And then you got the fabric. So on the fabric side, this has definitely got to be an IP address. These interfaces are all layer 3 on the fabric side. On the access side, it could be, it varies depending on what you connect. Okay, could be a layer 2 interface to another switch. Could be connecting to a server. When it's a layer 2 interface to another switch, you would have a VLAN. Okay. So When it sends traffic over the fabric port, it will always encapsulate it with the VTEP IP. Okay. Now, how does it handle the traffic? That's what it's saying. A is here, B is here. Local station table has an entry, B is on L5. And we'll call this L5 switch, this one. Okay. This would then be classified as a known unicast. Now, not local, sorry, should be global station table. Misspoke there. Global station table. Local would have the other entry. A is on 1/2, for example. That would be B. The machine B is classified as a known unicast. While if it's trying to talk to C and C is not in the table, it is known as an unknown unicast. Unknown unicasts are always sent to the spine proxy. More precisely, which IP? Not to a specific spine's IP, the Anycast IP. That means, hey, I don't care, talk to any one of them. Hash it onto the link so it speaks to any one of them. Okay. Then broadcasts and multicast. It says to a group VTEP that exists on any leaf with membership for the group. Now, typically, I should send that, flood these to the bridge domain. The bridge domain has a multicast address. It's called the multicast group IP outer address. Oh. So my B and M traffic is forwarded to that group address. And that address will exist on any leaf switch which has membership of the bridge domain. Okay. Now VTEPs, technically, most of the time you associate the word VTEP with a physical leaf. But there might be a circumstance where you may have a Cisco AVS, okay, now known as Application Virtual Edge, AVE, and this is a virtual switch, or kind of. I'll tell you why I use the word kind of when we go to that chapter of virtualization. Kind of like a virtual switch, and this would be a VTEP. Okay, that's what it says. Okay. That's why virtualization is so vast a topic in this particular class, because most data centers have too many servers which have become virtualized. Let's take a look at the packet flow. This one and this one. It sends any frame into the fabric or to the switch, any form of frame. Leaf 1, local station table, is going to have this entry. Now, whether it learns the MAC address, remember, every virtual machine or every physical machine has two identities. A layer 2 address, which is the MAC address, a layer 3 address, which is the IP address. Okay. So, since this is a leaf switch, remember, leaf switches have two interface types. They have access ports, in other words, ports facing endpoints. I'm going to say ports connecting endpoints. We have the fabric ports. Ports connecting to spine switches. Anything learned on access ports goes into the local station table. Anything learned via fabric ports goes into global station table. Okay, so local is locally attached. Global is remotely learned. Global station table is not called a cache. Global station table is termed as a cache. Now it's true this is populated based on locally attached learned entries, but those entries stay there for kind of like, I would say, as long as those devices are attached or they're still connected, those entries will stay there. Okay. And when the LST populates, as and when the changes in the LST, it sends updates to the spine. So my leaf switches are going to learn endpoints due to any form of frame coming in. They're going to populate the spine using Proxy, the spine using QoP protocol. Okay. Now, what does it learn, and does it bridge it or does it route it? Okay, it says packets are routed because this is I'll think about it, it's capable of switching, it's capable of routing. Packets are routed if the destination MAC address is a router MAC. That means if the ACI, its default gateway IP 10.5.3.1 is a default gateway. It's a SVI on the L1 switch, and it's got a MAC address. That's the L1 switch. That means this MAC address belongs to the L1 switch, which they otherwise call your router, right? If the destination MAC address is the router MAC, that means you have a frame coming in this way, and the MAC address has this value, that frame will be routed. That means it will make the decision by looking up IP addressing. Well, if it is not this MAC address, any other MAC address as the destination, they will be bridged. Okay, no time to live decrement, and of course, no MAC, and a MAC read write occurs. Okay. So that's of course one criteria. If the destination MAC of the frame coming in is the MAC address of the SVI. Switched virtual interface on L1, then it's going to route it. Any other MAC address, it's going to go ahead and switch it or bridge it. Okay. Of course, if you have any non-IP packets coming in, it's based on MAC address. ARP. You can see how the leaf switch receives an ARP request. As you may observe, it does not flood ARP. It uses the destination IP in your ARP header, I would say in your ARP request header, to perform a lookup. Okay. It finds, let's say, B in its global station table. B is on L5. Finds B in there. So then it takes your ARP frame, encapsulates it in VXLAN, puts the VTEP IP as destination of L5, and thus it sends it to L5 only, not flooding the entire bridge domain. Now, how does it handle device mobility? What happens? So you may have seen what it did. It changed your broadcast ARP frame into more a directed ARP by sending it only to a specific switch. That's why we will call it a directed ARP rather than a generic broadcast ARP. Okay. Any GARP, ARP, they are all going to be changed. Let's look at an example of a virtual machine that has moved. In this example, they've shown you that it's Hyper-V, so there's a virtual machine. I have to build on the context. In this example, we are going to pretend as if we had A and B on L1 and L2. We're going to pretend that. So according to the spine proxy table, A is on L1, B is on L2. There's another one I'm going to write, L1's global station table. GST has an entry saying B is on L2. Because there was already some traffic that went from A to B, so it cached. Remember, this is a cached entry based on past conversations. Okay. Now, so A and B were happily talking, and somebody moved the virtual machine using a live migration. In Microsoft, that's called live migration. They moved it here to L5. Okay. Now, typically, most hypervisor software, whenever a new virtual machine moves on to that particular hypervisor, it sends either a reverse ARP or a GARP or something. If it was a VMware, it would send a RARP, and here it's Hyper-V sending a GARP because the machine just moved. Okay. Now, once it moves, if it sends a GARP, of course, my L5 is going to detect, my leaf 5 is going to say, oh, I have B on port, whatever port this may be, 1/8. I have B on port 1/8. This will be the local station table. I'm going to write that very clearly. Of L5, it says B. Now, of course, that switch is going to send an update to the spine. So now it's going to cross over it and say, well, it's going to be an L5. Now, why does it only cross over? Because it is going to send a message back here to this switch. That switch had an entry. L2 had a local station table entry saying B was on 1/10. It had one because that's where B used to be. It had one entry. So now that the spine got this update, it's going to go ahead and send a message to L2. Right there, I'm going to update the message. That means, should anyone ever send you any frames for machine B, please bounce it off to L5. Okay, it actually marks it in the table saying you need to bounce it off. So now, if A were to talk to B, A's leaf switch has an entry saying B is an L2. So I'm going to say the frame goes technically, it would go from A towards L2 right there. What does L2 do? L2 sees a bounce entry. It says, well, I've got to bounce it off to L5. Okay, that is called the forwarding exception, because originally it thought and send it to L2, but now there's an exception bouncing it off again to another switch. It's a type of forwarding exception. Now, keep in mind, once it's received by machine B, B does respond back. When B responds back, we would expect that global station entry on L1 to be updated saying it's on L5. So any future frames will go directly to L5. They don't have to be bounced off of L2. Okay. The picture here is a little bit more better at explaining the two entries, the local station table and the global station table and the proxy table. This is an example of a proxy table on the spines. All IPs and all MAC addresses, all the endpoints, or all IPv4, IPv6 addresses of the endpoints are all in here. By the way, they should all be part of the same proxy address, so we'll just call it proxy A. The same Unicast proxy, so we'll just call it proxy AIP, and that's the station table. Here's a local station table for L1. Here's a global station table of L1. Okay. The size of this table maximum right now is 1.2 million entries, and that is applicable for 9516 hardware.
I have a question, Elizabeth.
Yes.
Actually goes back to the previous two slides. The size of the local station table that's mentioned is 1.2. Is that
no, not local? Only the proxy table I mentioned. That's maximum.
Proxy table. Is that per context or for the entire?
It's for the entire. It's not per context.
Okay. And I also have another question on the, I think it was page 75 in your slide when you're talking about the forwarding exception example that you shared with a bouncing.
Mm-hmm.
So I'm drawing a parallel to the legacy network. The entry in switch 2, in leaf 2, if you move that device, is it permanent, that entry, or is there a
Yeah. It will age out.
What's
It
the,
actually, it will age out. What this switch would do is, now keep in mind, this is a virtual machine, so the physical link doesn't go down. That's
right.
why I couldn't take that entry out. If it was a physical link and the link shut down, that would have aged out. That would have gone right away. But the reason it doesn't get rid of it right away is because it has to do, remember what has happened on L1, it has cached it.
Right.
So there are chances that there might be other switches also which have cached this entry. So that's why it doesn't age it out right away. Even when you, if it was a physical server, it knows that the link is down, but it will not age it out right away. It actually has a timer for this debounce saying, hey, keep this bouncing entry on for so many seconds.
Okay. Got it. Thank you.
Okay. The global station table does age out. If you haven't used it, it ages out in 5 minutes. So the maximum timer for the bounce entry that you can set is the max timer of the global station table. That's the max timer that you can fine tune for the debounce entry.
Okay.
Now here's Unicast Forwarding. It actually shows you packet is, where is it sourcing from? A virtual machine in a VMware environment, I guess. Or it could be a Red Hat. I frankly cannot tell you that this could be a Red Hat or VMware environment. They all, both of them support industry standard VXLAN. So it appears that it's being received. This is an industry standard header. We're going to pretend as if that virtual switch does VXLAN encapsulation. That could be VMware or Red Hat, KVM. And then of course, this is the access port right here. So as soon as it's received, the first thing the ACI switch is going to do is, hey, I've got to put you into an EPG. Okay, I'm going to categorize you into an EPG. Then and only then, I'm going to identify which EPG you belong to. Then and only then, I'm going to go ahead and put the VXLAN header around to make sure I can forward you within the IP fabric. So in here, has to be VXLAN encapsulated. Okay, so it strips the standard VXLAN. It may assign in the header. So one of the fields here is the source group. That means source EPG. The source EPG might be based on the VXLAN header. So it may assign it to web or app or whatever, source EPG. Assigns a VXLAN ID based on the VXLAN that it's being transported on. That's the crucial. Where does it send it? Okay. So where should it send it? Well, that's the question. That depends on, has the leaf learned destination IP? Does this leaf have it in the global station table? No. Does it have it in its local station table? Well, then it can just, yep, if it's local, it just sends it to another port on its, it doesn't have to send it through the fabric. Then it's not doing it, it's just switching it locally here. Okay. If it has to send it to another device, another switch, which means through the fabric, it has to have these headers. If it has already learned it in the global station table, the destination VTEP equals the destination leaf. Direct forwarding, if the incoming leaf, the ingress leaf, has learned the inner IP, that's the inner IP, where this is the inner IP, to the locator binding. It already knows about it in its global station table, send it there. Well, the other scenario, don't know about it, we need to send it to the spine. Forward it to the spines. That means the spines will need to do proxy table lookup. And don't get me wrong, hey, even if the leaf had it in its global station table, that means if this was met, this condition was met, physically it still went through a spine problem. Definitely, not probably. Physically it's still going because everything connects physically through a spine. Every leaf. There's no way two leaves can talk to each other. Now, of course, if this condition was not met, it is sending it to the IP address of the spine. This does a spine proxy lookup. That's the few milliseconds, but it's done in hardware. So pretty much no penalty, no latency. And then it swaps it out with the IP address of this one. Okay. So of course it now makes its way here. Now in this particular example, there's Microsoft's Hyper-V server using NVGRE encapsulation. So here it was a standard VXLAN, egress out, ingress was standard VXLAN, egress out with NVGRE, it goes ahead and sends it to the virtual switch, which sends it to its corresponding virtual machine. So it's a given that when the frame is received, the source group is going to be determined, EPG. On ingress. That's what is programmed into that header there, the source EPG. Now, how do I know? This is a web EPG and the destination is a application EPG. Should they communicate or not? What if this is a web server? This is an application server. How do I know? Is it permitted or not? Okay. So packets on ingress, the first thing it does is determine the source group. Always going to determine the EPG. It could be based on the physical port that the packet comes into. It could be based on the VLAN that it is in. It could be based on the VXLAN. That's an industry standard VXLAN. Okay. It could be based on the IP address of the packet. It could be based on the subnet of the packet. It could be based on a virtual machine name. Okay, so it identifies the EPG and sets it in the header. Now, understand that if it does know global station table, does it have the destination in the table or not? If it already knows the destination, it also knows, so it's not a question mark, it already knows destination is on leaf 5. So I'm going to pretend I'm going to write in there that the destination so it basically knows, then it also knows the EPG, because that's how it caches it. Everything it learns, local, global, it always knows the corresponding EPG. If it learns it in the table, it knows the EPG. If it's not in the table, that's a whole different story. So if it's there in the table, and this is a web EPG, this switch is going to go ahead, look up its policy. Who pushes the policy? The APIC pushes the policy to the switch. So the switch is going to go ahead and say, is my web EPG allowed to communicate using this protocol to the application EPG? Is permitted or denied? If it is denied, drop it right away. Don't bother sending it towards the firewall in the contract. Don't bother. If you already know, drop it. If you don't know, what are we going to do? Well, through the spine, apparently the contract that is configured between the web and the app seems to have a firewall. So it goes through the firewall, firewall permits it, and it makes it to the app server. Once it gets there, because it was not, the destination is not in the table, that's why it has to make that effort, get it here to L5. L5 is now going to do, hey, do I permit from this source, which is the web EPG, to the local, which is the app EPG? Do I permit it? Okay. Now, there are some things that take place when the frame has to go through a service, if your contract has a service graph. It will first send it to the spine, of course, based on the contract. It will chain the IP to the firewall's IP, the destination, send it to the firewall, and then, of course, send it towards the final destination, where it may just drop it. We don't know. That depends on the policy. There's always enforcement policy being done. The best opportunity, ingress. If it's not done on ingress, it will be done on egress. Okay. There's a field in the header where it actually tells it whether the policy has been enforced on ingress or not. Okay. Now, source is always identified the minute the frame is received by the ingress switch. Destination is the big question mark. Okay, so implementing the policy at the source is the default. It is considered the better opportunity. No point in sending the frame all the way to the egress switch and then the egress switch drops it. That's a moot point. multicast packet flow, rendezvous points. This is actually showing you a classic multicast environment. Okay. So classic multicast environment, you have your contrast being drawn between a classic and a Cisco ACI multicast environment. By the way, what is SG and star G? What is that? In multicast, what is S comma G and star comma G? Anyone familiar with that? Those terminologies in multicast. That this has got nothing to do with ACI, by the way. Purely multicast technology.
It's source group.
Okay, source comma group and any source comma group.
Any source group. Yep.
Okay, so any source, that means the multicast environment does not specify which device should be the source for that multicast. Application, S comma G, we're specifically mentioning who is the source, from which source the receivers, the clients would like to receive from. Okay, now in a classic network, we really don't know how many hops and devices, how many hops devices are away from your clients called your receivers. Could be 5 hops away, they could be 2 hops away, it could be 3 hops away. So it's not like an ACI environment where everything is basically always 2 hops only. You have your receiver here, and you have your source here. Well, it's always going to be 2 hops. There is absolutely nothing other than, if I count the ingress switch, it's 3 physical hops. It's always going to be the 3 physical hops. Okay. So, whereas in a classic environment, you can have the source and the clients, they call the receivers, multiple hops away. So if you have a specific application where your receivers always want to get their multicast from a specific source, these devices have to maintain it. That's called maintenance of the SG state. It starts taking memory. Okay. Now, in a traditional multicast environment, we do need PIM, multicast routing protocol, inside the fabric like PIM. Here, even though this is an IP-based fabric, okay, if you're multicasting in a bridge domain is a flooding domain, you're multicasting by 2 subnets in there, you don't really need PIN. You do not need the routing. Now, if you're multicasting between bridge domain 1 and bridge domain 2, you would need PIN. Okay, but devices in bridge domain 1, even though they are 10.5.3.0 network and 10.5.4.0 network, no need of them. They're in the same bridge domain. So there are some advantages to running multicast. It's easier to handle it, okay, in an ACI environment. The only thing we depend upon is IGMP. And even ISIS has stepped up its game to take care of multicast. Okay. It tells you that all multi-destination traffic, I'm going to rule out this. This is only used if you have disabled hardware proxy. That means you've said don't use the spine proxy, but go with the forwarding trees. Only in that case, you basically have the concept of having to depend on the, for unknown unicast, we don't depend on the forwarding trees. I'm going to take a look at an example. That's an example of there are actually possibilities for 16 parallel trees. Okay. And each tree is rooted at a spine. So that's a spine in this example. We can see that these are receivers, by the way, all of these, no, these two are not. As you can see, these four are receivers. So it's every receiver sends IGMP. So it comes in on certain ports here. Of course, these switches are snooping for IGMP. Okay. And they identify which multicast address these IGMP join messages are for. That's part of this. And then ISIS will basically identify the EPGs, corresponding bridge domains that these are on, and every bridge domain has its own reserved multicast address. Every bridge domain has its own reserved multicast address. Okay, so technically, what I am actually emphasizing is broadcast and multicast. They utilize one of the 16 parallel trees that are calculated for flooding purposes. Now, we'll pretend as if these are all members of a bridge domain 1, and they are assigned reserved multicast address to, I think it's a 232.1.1.5. All of these are members. So each of these not the third one, four, 5, and 6, they are going to join this group address. And once they join, because they're members of the bridge domain, once they join the group address, they decide to use one of the trees. So we actually have 4 spines. That means possibly at least 4 trees. They decide to use this for any flooding of 232.1.1.5, any flooding for this bridge domain. So if you have a multicast frame coming in and it's to be flooded, the VTEP outer IP, that means when it sends it in VTEP, it sends it with this address as the outer address. This route is going to go ahead and send a copy to every switch that's a member of or provided a join membership for this group. Once it gets to each switch based on the IGMP join messages. So these it send the IGMP joins certain ports. And the IGMP join was not for this address. It was for the data plane multicast address. So the switches will send it out to the respective ports based on the IGMP join messages. Okay, so remember, inner address will be the data plane multicast. The outer address will be the bridge domains multicast. Because every bridge domain has a reserved multicast address. The policy enforcement, even for multicast, is a little different. They are not the same as unicast. Okay, you can have your receivers belong to multiple EPGs. They don't depend on the unicast contracts. The group admission, membership into any data plane multicast group is based on IGMP joins. So here it actually shows you why do we have multiple trees. So you can load balance. Different multicast floodings can be routed across different trees. Your ingress leaf is going to decide, should it send it to root of tree 0? Should it send it to tree 1, tree 2, tree 3? Then based on the forwarding tree. Multiple trees give you potential for load balancing. The trees are computed and advertised using ISIS, the 16-bit field for the number of trees, not 16 bits, sorry. I should say 2 to the power 4, 4-bit field, so it's 16 trees. But at this point, we support only 12 right now. 12 simultaneous trees are computed. The outer IP is the bridge domains IP, which is a multicast address. The VTEP IP. The last 4 bits, of course, of that IP is used for the tree number. Identifies, in this case, that's where it's sending it. You may notice it says group IP outer address membership. How does it know which switches are part of which bridge domain? That's computed by ISIS. Which devices belong to which EPGs? EPGs are in which bridge domain? Which nodes? Because you can easily unplug something from here and move it there. EPG changes, bridge domain changes. So all this is shared by ISIS. Okay, and the fact that these 4 switches belong to a certain bridge domain identified by ISIS. IGMP either sends join messages or leave messages. Now, for example, here's IGMP report originator. That means it's a receiver, a multicast receiver. It seems it's not able to send a join. It's denied from sending a join. The reason is, of course, you've created a multicast policy saying certain devices can send join messages to certain range of IPs. Okay. It's a special handling It doesn't use the one for unicast, the special handling for multicast traffic. Your source belongs to a regular EPG, and you can tell it which range of multicast addresses it can send multicast streams to. Okay. They're always going to follow the IGMP join. Of course, since it is multicast, it tells it not to follow the regular unicast enforcement. It puts a field in there to bypass the policy enforcement at egress, because it's always set at ingress. Right there is, of course, the behavior. All broadcast and multicast is treated in a similar manner. They are encapsulated within the group address of the bridge domain and sent out. Let's look at the summary of Intra-Fabric forwarding within the fabric. How does forwarding take place? Where is the packet coming in from? Right there, packet coming in. Okay. So it's checking, is it a layer 2 or layer 3? Is it a layer 2 or layer 3 frame? That's the first thing. Is it layer 2 or layer 3? How does the switch decide should it consider it as layer 2 or layer 3? Well, if the SVI, that means the router's own MAC address, some MAC address assigned to its SVI, or I would say switch own MAC address. Then it's layer 3. Everything else, layer 2. Okay, so in this, they've expanded on the discussion of layer 2. It says, if it is this, look at layer 3 forwarding. And we're going to see layer 3 forwarding. But we'll pretend that it's not the SVI of the switch itself. So we'll look at layer 2. Does it know the destination back? If it is, yes. Is it local? To send it out through the local port. Okay. If it's not local, that means it's in the global station table. So send it out towards the remote leaf. That's if it knows. If it already knows the destination MAC, then go about the left-hand side. Well, if it doesn't know, then it's classified as an unknown unicast. Okay, so that would be an unknown unicast. What's the configuration of the bridge domain? What's the bridge domain set to? How does it handle a non-unicast? If it's hardware proxy, send it to the spine. Does the spine know the MAC address? I just send it if it knows it. If it doesn't know, drop it. That is if you've set this is the default approach. If you've changed it to flood, then it's going to flood within the bridge domain. And then, of course, hopefully it reaches the remote leaf. And then the remote leaf will send it to the required device. Okay. Same thing. Let's continue with, where was that? Intra-Fabric forwarding. Packet coming in to the leaf. Do we have unicast routing enabled in the bridge domain? That's the question. Now, let's look at what happens. I would specifically change it that this is an ARP request packet, okay? So you want to just remember this is very specifically for ARP, not just any packet. It's an ARP request packet. Okay, so now do we have this? This is, by the way, enabled by default. This is the default setting. If that is turned off, it says just flood it. Flood it in the entire bridge domain. That means send it to all the switches by using that multicast tree. Okay. Now, if this is turned on by default, it says, is the target IP address in our payload an ACI pervasive gateway address? Is the target, remember, in your ARP request, you always have a request specifying the IP. ARP for a certain IP, right? That's why it's looking at the payload of ARP and it's trying to determine who you're ARPing for. So this IP, is it an address defined in the ACI network? That means when you define the ACI configuration, when you configure the bridge domains, you're going to specify what is called the default gateway addresses for the bridge domain. It's asking you, yes, is that IP an address which is the default gateway of the bridge domains? Leaf intercepts it, goes ahead and sends a reply. Okay. Now, know what's the status of ARP? Is it enabled for flooding? If it is, hey, just flood it in the bridge domain and it gets to the corresponding switch and the switch will ARP it out to all the ports. Well, if flooding is not enabled. Okay. Does it have it in the global station table? Is that IP in the global station table? Forward it to the right leaf, and then the egress leaf will flood it to the ports. If it's not in the global station table, send it to a spine proxy. Does the spine know of it? Yes, just forward it to the leaf, and the leaf will flood it, and hopefully we'll get the ARP response back in Unicast. Spine doesn't know about it, not what it does. It says, drop the ARP request and glean. Oh, the spine is going to go ahead and say, I should send out an ARP as if I'm the originator. Okay, the ARP glean is essentially saying the spine is going to drop the ARP from the originating device. It'll generate a new ARP with pretending to be, will generate a new ARP request with the originator being a bridge domain's gateway address. It'll send it to all the leaves in that bridge domain. And then the leaves will all get it, and they'll send that ARP to all the local ports. And hopefully once they get ARP sent out through the ports, it'll get a reply, and then the co-op table will eventually get populated based on the response. Okay. The word glean means drop the originator, send it out as if the spine is going to go ahead. It's going to originate a new ARP, but as if it's the switch which is sending a request. The leaf switch. The gateway switch sending a request. That's how it originates it. Now, back here, it said if the packet is coming in and it determines that it's for a MAC address of the SVI, it determines that. That means it's going to do layer 3 forwarding. So here is layer 3 forwarding discussion. Okay, it comes in. Notice destination MAC is the ACI MAC address, that means the MAC address of one of the default gateways. Does it know the destination IP as an endpoint? If it's a yes, is it local in the local table? Send it to the port. If it's a no, we're going to presume it's in the global station table and send it to the remote leaf. Okay, does the leaf know the destination IP? Versus what were we doing here? Does the leaf know the destination MAC because it determined that this was a layer 2? This slide was particularly, they should have corrected it and said it is for dealing only with ARP. It's an ARP packet. Okay, that's particularly focusing on ARP frames. This is now looking at the destination IP of the packet, not known to your ingress switch. It says, does the leaf have bridge domain subnets for the destination IP? That means, do we have it configured in any of the bridge domains, these subnets? Yes. Send it to the spine. The spine will hopefully find it in the table and they'll forward it. And if it doesn't, it'll drop it. And then again, the spine will do a glean. That's as long as the subnets are defined. Not defined, has it learned of these subnets through some external. So your leaf switch is connected to, let's say, a Nexus 7K, which is sending routing updates. This would be considered an external layer 3 route. Receiving any routing updates from here. It's asking, does the leaf know any the destination IP as a layer 3 route? No, just drop it. Yes, send it to the physical leaf that is connected to the layer 3 device. And it need not mean this leaf is connected Nexus 7K. It could be another leaf. So it's going to send it here. And then if that's physically connected, it's going to go out that way. The border leaf is the leaf that's connected to your layer 3. And that basically brings us to the end of that chapter.